看一看啊，哎，去厕所了呢，泡泡呢？
So good morning, everyone. So I think it's 9:30, 9:10 now. So we will start a workshop. So I say good morning for Europe, good afternoon for China, and I think now it's too early to say good morning to America now. So thank you very much for coming to the Microalgae biotechnology workshop. So we this workshop is about the discussions on microalgae biotechnology for biofuel production and environment application. So my name is Shimin Zhan. I'm a professor in civil engineering at National University of Ireland, Galway. So I'm a principal investigator of a research project funded by SAI. So SAI is Sustainable Energy Authority of Ireland. So this project is about, I use microbial biotechnology to achieve wastewater treatment, biofuel production, and also greenhouse gas mitigation. So so before we start, I will say some house rules. Sorry, I just see how to go to my computer to see how to. Okay, so one that you are muted by us automatically. I hope for audience, please keep muted because we don't want to see any background noises affect the presentation. And also, yeah, so we have muted you, so please don't unmute it. Okay. So we have helpers to maintain the order, but sometimes because too many participants, so it's difficult to check everyone. So please unmute it. So if you want to ask questions, so please type your questions in the chat function, okay, on the Skype. So we have PhD students to record your questions. So if their time, the time available, then we, I will. Yeah, sorry, please unmute everyone, please. So we will ask pass the questions to their speakers so they can answer your questions. But if the time doesn't allow, then I could ask you for the question to the speakers after the presentation. And also we have for this presentation, for this workshop, we have two live stream channels. So one is on YouTube. This YouTube live stream channel is for for audience outside China, and then we have another live stream channel. Okay, this is on co-share. So this is for audience in China. So it's very interesting to see that now there are two parallel worlds now. Yeah, so the links of this live stream channels, we have put on the chat. So you can go to a live stream channel. For example, if because like now is the evening time, so in China. So if you want to go to cooking, you can still join this discussion and listen to the presentation through this live stream channel. So this morning, actually, we have a quite a busy schedule. So we have 10 presentations. So these 10 presentations, we 7 are given by experts from different areas in policy making, in research, and also in industry. So this expert from Ireland, from Spain, from UK, and from Portugal, from America. So they will share their experience with us. And also there are 3 presentations given by my own team, so they will also present some interesting results we have got from our research. So just another before I finish, I say that today this will be the schedule. So after the presentation, then we will have a panel discussion. So this panel discussion will be chaired by and also we have co-PI of this project. Anyway, so now we will go to our first presentation. So I will exit my share screen. So our first presentation is given by Mr. Mahon. Mr. Mahon. So Conor Mahon is a program executive in the heat and bioenergy team in the Sustainable Energy Authority of Ireland. So Conor has worked on in life cycle assessment and also sustainability for heating, different heating options. So Conor has contributed to the recently released national heat study. So today it's great we have Conor here to present biomass fuels in Ireland. Okay, very much, Conor. So I pass this to you.
Thank you very much. I'll just first check, just as we're on Zoom, that you can hear me and the presentations up.
Yeah.
Yep. Perfect. Thank you very much for inviting me today. My name is Conor Mahon. I'm a program executive in the Heat and Bioenergy team in the Sustainable Energy Authority of Ireland. Today, my presentation is going to look at biomass fuels in Ireland. And in particular, I'm going to look in heat. So the format of the presentation is going to be a background on biomass fuels in Ireland. The majority of it is going to be about the recently released National Heat Study. Then I'll talk about the Renewable Energy Directive before talking about the SEI research and events that are upcoming. And then finally, just some conclusions on the overall report presentation. So on my first slide here, it's just a background on biomass fuels in Ireland. Ireland imported 77% of its energy supply in 2021, up from 72.1%. However, 91% of Ireland's renewable energy is indigenous. This isn't 100% as we import the majority of our biodiesel and bioethanol and some of our biomass. In a time of increased energy security awareness due to global events, I think this statistic highlights the role of renewables in energy security. But to continue to improve energy security, we need to continue the development of indigenous sustainable fuel pathways. Bioenergy collectively accounts for 32% of renewable energy in 2020. There's a trend seen throughout Europe where bioenergy makes up a significant proportion of renewable energy, and it just indicates the large impact that bioenergy has in meeting renewable energy targets. Direct use of biomass represents 5% of Ireland's heat demand. This share has grown slightly over the past decade, mainly in industry. While bioenergy makes up the majority of renewable heat, there is room for expansion, as I'll talk about later. So next, I'm just going to talk about the background on renewable heat. Heating represents 38% of energy-related CO2 and 24% of total national greenhouse gas emissions. As you can see on the left there, it's comparable to heat or to electricity and to transport. The graph is just to show that without decarbonising heat, it's going to be very difficult to decarbonise overall. And you can see from the graph, annual emissions from heat have actually increased since 2014. This is compared to electricity, which has seen quite a large drop off in that period. On my second graph I have here is from the Renewable Energy Directive target, and this is our progress to this target in 2020. As you can see, we did not meet the target, mainly due to a lack of uptake in renewable heat. As you can see, progress was made in transport and electricity, but heat lags far behind. 2 points here. There's obviously clear barriers in heat, and there's also a lot to learn from transport and electricity. Which brings me on to the main portion of the presentation today, which is the National Heat Study. The SAAI commissioned the National Heat Study to provide an evidence base to support Ireland's climate action targets, and the findings have been used to support Ireland's second submission to the EU of a national comprehensive assessment of potential for efficient heating and cooling as required under the Energy Efficiency Directive. However, the study has gone well beyond what would be normally expected of that submission, which brings us nicely to the slide now about the heat study model. So the heat study was separated into 8 additional reports released alongside the summary report. The actual model is very comprehensive, involves analysing the total supply, cost and greenhouse gas emissions of sustainable heating options. Today is just going to be a summary of the heat study, but I would recommend for everyone just to, if you have a certain thing you want to look at, separate it into 8 reports and just to do a deep dive. There's some great information in there. The model used 680 individual heat demand archetypes, representing a combination of physical and consumer attributes, which has given it a very detailed description of heat demand. On screen there, you can see there's 5 scenarios outlined in the summary report. At the very top there, the baseline scenario is based off the 2019 Climate Action Plan, and then we have 4 additional net zero options with different policy emphasis investigated. These are high electrification, decarbonised gas, a balanced scenario, and a rapid progress scenario. The study was completed in consultation with many stakeholders, and the emphasis was put on its practicality, so it could inform policy in the best way. So this slide is slightly difficult to go through in a presentation. I'd recommend anyone to maybe, if this presentation has been sent around, to go into more detail on this one, or it's in the summary report of the heat study. But in essence, the slide shows technologies seen in the 4 net zero scenarios. While different scenarios see expansion of different technologies. For example, if you look at the decarbonised gas on the bottom left, hydrogen has a much greater uptake than in the other 3 scenarios. However, there is some common themes that are seen throughout. For example, district heating, which at the moment is not a common technology in Ireland. It is common in Eastern and Northern Europe, sees great potential. is proven, available now, which is important in the context of 2030 carbon budgets, and analysis suggests that it could provide up to 50% of building heating demand in Ireland. Just on the topic of carbon budgets, just an important note I've put in here, that while heat doesn't have a specific carbon budget, it does affect, along with bioenergy, each of the sectors. If the cuts required in the carbon budget were applicable to heat, none of the 4 scenarios would meet the 2025 budget, and only the rapid progress would meet the 2030 budget. I've just put that in there just to highlight the large scale of the task to decarbonize heat and the large intervention that's going to be needed over the next decade. Other themes I pulled out here from the heat study include the prominence of heat pumps, the need to decarbonize the electricity grid, and on the next slide, I'll talk about the bioenergy themes. So this slide describes the bioenergy themes in the heat study. From the table, you can see that I've pulled out the uptake of bioenergy split into 3 categories across each scenario. The main highlight in bioenergy from the heat study is that the model has shown that bioenergy meets a significant portion of heat demand in all scenarios. Between 7 and 17% of heat demand is supplied by bioenergy in 2030 and a similar amount in 2050. So we're going to see, we're more than likely going to see a higher uptake of bioenergy over the next decade. The difference between scenarios, as you can see there, is based on land use for energy crop cultivation. For example, the rapid progress scenario has the highest availability of domestic resource because of the assumption that there's additional land use change from beef farming. In layman terms, the rapid progress scenario is the only scenario where there is a reduced herd reviewed. The other 3 scenarios assume that there'll be a stable herd. All available low-cost domestic bioenergy resources that are generated by other non-energy activities are used. There's 2 points here. There will be an emphasis on low-cost domestic bioenergy resource. However, there's also going to be a limit to that, as these are going to be waste and residues of other industries. So we'll be reliant on what the other industries do. The domestic bioenergy resource considered in the study was around 6.5 terawatt hours in 2020. Just over 2/3 of this resource were utilized in 2020, suggesting that there is a large scope for increase. And just my last point on this one is between 6 and 15% of heat demand in 2050 is delivered by heating systems using carbon capture. Post 2040, we assume that bioenergy carbon capture deployment in all scenarios, and this is really just very hard to decarbonize industries. So here on this slide, I've just pulled out the key conclusions that relate to bioenergy. There are more conclusions in the report, but just for the sake of time here, I've just pulled out those related to biomass fuels. So the first and one of the main conclusions was to plan and prioritize district heating deployment. It sees a wide uptake in all of the scenarios apart from the baseline. This is related to bioenergy because this district heating sees an uptake of waste heat, heat pumps, and biomass. In the bioenergy sense, this is especially important in local areas with a large bioenergy resource and with the required heating demand for district heating. The second conclusion is that we require a nationally appropriate sustainability governance, which is there to minimize upstream emissions, align with circular economy, and bioeconomy and avoid increasing emissions in non-energy sectors. As I spoke before of the domestic bioenergy resource that's available, there will have to be some type of monitoring just to make sure that by the uptake of bioenergy, it's not affecting other sustainability factors. And the final conclusion I have here is the availability of sustainable biomethane is linked to land use choices and requires increased productivity in the agriculture sector. Biomethane can be a competitive option if the costs and benefits are shared across the gas grid, or if used off-grid to displace oil. So just moving on from my previous point on the nationally appropriate sustainability governance, the Renewable Energy Directive has been recast to the Renewable RED II, introduced to cover the 2021 to 2030 period. The headline renewable energy target is 32% from renewable sources, with a possible upwards revision. The main point on biomass fuels is that it's introduced a mandatory sustainability criteria for solid and gaseous biomasses in things like indirect land use change and updated greenhouse gas emission savings for bioenergy, as listed there on the screen at the bottom. For example, fuels with high indirect land use change are limited to 2019 consumptions initially and then reducing. It's also introduced additional requirements for transport biofuels as well. So the biomass fuels RED II requirements are initially applicable to new installations with a fuel capacity equal to or greater than 20 megawatts for solid biomass, and equal to or greater than 2 megawatts for gaseous biomass. However, RED III proposals are to lower the minimum threshold to 5 megawatts, and it's also been suggested to apply it to existing installations. This would be a major expansion of the coverage of biomass fuels under the directive. But the overall conclusion on this slide is the policy signal is clear that there's a greater emphasis on monitoring sustainability and quantifying greenhouse gas emissions for bioenergy. Advanced biomass feedstocks like algae tend to have lower greenhouse gas emissions, less sustainability concerns such as indirect land use change risk compared to more traditional bioenergy, so should see a greater interest once this is introduced. However, it is important to note that when analysing bioenergy pathways, sustainability, greenhouse gas emission reduction should be at the centre of these pathways. So just before I finish up, I just want to give a very quick plug to some of our research and events that's coming up. First of all, with the project here today, we're delighted in the SAI to support these type of innovative projects such as the NUIG Galway team today. Unfortunately, one thing I would say is our 2020 RD&D call was closed this week. However, please do follow our website and our social media to stay aware of any future research opportunities. In 2022, 20 million is to be invested in research supporting Ireland's transition to clean and secure energy future. It includes a list of topic strands and open strands, and all the information is on the link here. And let me know if the slides aren't being sent around. I can put this on the chat otherwise. And the other thing I want to talk about was SAI Energy Awards that have just been relaunched for this year. And in particular, because I know I have quite a lot of researchers on the line today, is the Excellence in Energy Research and Innovation. This award is aimed at organizations that have researched and developed innovative energy-related technologies, processes, or systems which will contribute significantly to Ireland's clean energy transition. The winner will receive a €10,000 bursary. Applications are welcome from companies, third level education bodies, public sector bodies, and semi-state bodies that are involved in impactful energy research and innovation. And the closing date for submissions is 5 p.m. Friday, 17th of June. And again, there's loads of information on the link there on the screen. So if you do have any questions, there's loads of contact details there. Or if you have any questions at the moment, please let me know. So being mindful of time here, I'll quickly run through our conclusions for the presentation. Decarbonising heat is going to be necessary if we're going to meet our 2030 and 2050 targets, and there'll have to be an improvement on the progress that's been made so far. The heat study model sees a key role for bioenergy. All available low-cost domestic bioenergy resources that are generated by other non-energy activities are used, which means there's going to be greater uptake. However, these are limited. Nationally appropriate sustainability governance is required. And again, as I said, for anyone looking at bioenergy pathways, RED 2 compliance and what's coming down RED 3 should be at the center of any project. And thank you very much for listening to me today. I don't know what format, if we take questions now. I'm happy to.
Yeah, Connor, yeah, thank you very much for your keep time so well. So just one question actually from the audience. So I think we have time for one quick question. So Dr. Wagner asked, why is biomethane biogas expected to reduce from 2030 to 2050 under all scenarios? Is this due to diversion of biogas to other sectors or overall reduction in use of AD technologies?
So sorry, I just caught the end of that one. So it's the decrease of biomethane.
Yeah, I see from your the four scenarios. There's a reduction of biomethane biogas uptake, reduction from 2030 to 2050.
Yeah, so it depends on each scenario. So in the decarbonized gas scenario, is hydrogen is coming in there because a lot of the gas, there will be some injection of biomethane into the gas grid. So at that stage, it'll just be going off grid. In the electrification scenario, it'll be there'll be more electric heating. And on the baseline scenario, I think it's a mix of the two, but it'll be more going to off grid. So the move will be to more off grid use of biomethane.
Okay. Yeah. Thanks, Connor. Yeah. So yeah, thank you very much, Connor. So very interesting presentation, and also I'm very happy to see that you see things that Microalgae technology can play important roles in the sustainability and the greenhouse gas emissions. Yeah, thanks. Okay, so we'll move to our second presentation. So the second presentation is given by Mr. Shane Malone from biofuel obligation schemes of Ireland. So Shane will talk about the biofuels obligation scheme. So Shane is he's a project manager of the biofuel obligation scheme of Ireland, and he's a chartered engineer and a fellow of engineers Ireland. So he has a lot of experience in the design, implementation, and administration of projects in the energy sector. So Shane, so the floor is yours.
Thank you very much. Just to double check, you can hear me and you can see the slide.
Yes, very good. Yeah.
Great, thank you very much. Thanks for inviting me here today. It's a pleasure to talk to you all. As you've introduced me, I'm Shane Malone. I work for an engineering and management consultancy called Byrne O'Clerig. And we've been assisting the National Oil Reserves Agency with administering the Biofuels Obligation Scheme since 2010. So we've been doing it for a while now, so hopefully I'll be able to impart some wisdom onto you about how it works and what it's all about. One thing to note at the very start is, as opposed to Connell's presentation, which is very much focused on heat, this presentation, the BOSS, is very much focused on biofuels in transport. Let's go on to the next slide here. So just some background and some important things to note. The Biofuel Obligation Scheme, the BOSS, was introduced by the BOSS Act back in 2010. And this first extract from the BOSS Act, I'll just go through it slowly because it's important. It's that every oil company and consumer are liable to pay the levy. So it's companies in Ireland that are liable to pay a NORA levy. The levy is payable on every litre of oil placed on the market. And that levy is used to fund Ireland's security of oil supplies. So under International Energy Agency rules about joining and EU membership, member states are required to hold 90 days worth of oil stocks in the event of an oil supply shortage. So there's a link here in the BOSS Act to those companies that are storing or putting on the market fossil fuels, and specifically gasoline and diesel that's put on the road transport market. So it's those companies that pay the levy are required to ensure that a certain percentage of the diesel and fossil petrol they put on the market is biofuel. And that's what that fundamental tenet of the Biofuel Obligation Scheme is. And the biofuel obligation itself is a volume-based obligation. And as you can see here, it's increased steadily over the years since 2010, gone from a 4% blending obligation up to where we stand today at 13%. As I said, it applies solely to road transport fuel, even though the Renewable Energy Directive itself, as Connell referred to, also includes rail. In Ireland, we just have an obligation on road fossil fuel. As I said, it's administered by the National Oil Reserves Agency. Some of the legislation that's important in the context of the BOSS is it all fed out of the Renewable Energy Directive, which was published in 2009. And that directive set a lot of targets for renewable energy in general for member states. But the specific one for biofuels was a 10% renewable energy target in transport. It also defines importantly what the sustainability criteria for biofuels and for bioliquids are in the EU. So if a biofuel does not meet the sustainability criteria, it cannot be counted towards renewable energy targets. This directive was transposed into Irish law by really there's very many pieces of legislation, but two fundamental ones. One is the Energy Act, or the BOSS Act, and it set up the rules and requirements around the Biofuel Obligation Scheme. Who participates, biofuel obligation certificates, what are they worth, what are biocharges, trading certificates, all the framework surrounding how the BOSS operates is set out in the Energy Act. Then in 2012, there was the introduction of the sustainability criteria, and I'll touch on those later on. In parallel with all the Renewable Energy Directive requirements, there's also a greenhouse gas carbon intensity emission reduction target of 6%. I won't talk too much about that, other than to know that there is two schemes here running in parallel. The main one is the BOSS, and it's supplemented by a greenhouse gas intensity reduction target. So very much an overview of how the system works. I'll just get a highlight here. So the BOSS, it's an online system, the Biofuel online system. It has two operating systems. It has over here, it has the red, the Renewable Energy Directive, and it deals in certificates. And it's a renewable energy blending requirement. A certain percentage of renewable energy is required to meet these obligations. We deal in certificates. There's also double counting of certain biofuels if they're produced from waste and residues or algae. There will be a 2% limit on crop-based biofuels in future years. And I'll talk on the advanced biofuel target in a while. There's also a 3.5% specific sub-target for advanced biofuels by 2030. On the other side of the BOSS, we have the Fuel Quality Directive, and it talks in carbon intensity reduction targets. It doesn't have double counting. It doesn't have limits on targets for advanced biofuels. But what it deals in is in carbon savings. So it's reliant solely on carbon intensity of the fuels. And the companies comply with both of these requirements by trading certificates and carbon savings. So all of these account holders, which are the obligated oil companies, have obligations to meet. And they meet those by certificates and by carbon savings. And we rely on data submitted by the oil companies in the form of this OLA data here, which is data on the quantities of fuels placed in the market every month in Ireland, and also on specific sustainability information, which includes, for example, the carbon intensity of fuels, where the feedstocks came from, what are the biofuel feedstocks. Optionally, we also have allowances for electricity used in road transport to claim carbon savings, and also upstream emission reductions, which are carbon saving projects implemented upstream of fossil fuel refineries, or if projects are undertaken to reduce greenhouse gas emissions, those carbon savings can be claimed and offset against the requirements of the Fuel Quality Directive. So we're talking about biofuels, and really a fundamental question is, what are biofuels? And it's anything made from a biomass. It could be grown on land, such as rapeseed. It could be corn, wheat, barley, which are all part of the BOSS in Ireland. And what's important in Ireland is those biofuels produced from wastes and residues, specifically used cooking oil and tallow. And there are other wastes and residues that I'll touch on in a while. And the next slide we'll see, since the inception of the BOSS, what are the feedstocks that have been used to make the biofuels that have been placed on our market. Anything below this dark blue line here, these are all ethanol-based feedstocks. Anything above here are biodiesel feedstocks. So we can see we can have quite an array of feedstocks that have been introduced over the years. And we can see from this slide that in 2012, we more or less had a 50-50 breakdown in biofuels between bioethanol feedstocks and biodiesel feedstocks. But as we've progressed over the last decade, and you may know in Ireland, we've become very much a diesel-orientated transport market. Obviously, biodiesel has followed that trend and is becoming more important biofuel in the market in Ireland. And specifically, you can see here, which is obvious from this plot, is the growth of UCO-derived biodiesel. It makes up a significant portion of the biofuel market in Ireland, and we have a huge reliance on it, primarily because it is double counted. And I'll talk about that shortly as well. But we can see the range. We also have category 1 tallow, also makes a significant contribution. And in more recent times, this one here, SS, is waste starch slurry. So from the production of food products, it's used to produce bioethanol. And then also we have whey permeate, which is a byproduct of the cheese production industry, which is produced indigenously in Ireland. So that gives you a flavor of the makeup of Ireland's feedstocks. And if we look at the actual quantities that have been involved, this is the 2021 data. And we've broken this down by the fuel types themselves. We have bio-CNG, biocompressed natural gas, or biomethane, and it's 4 feedstocks that have been placed on the market. We have bio-LPG, we have the CHVO and HVO here, which is co-processed hydrogenated vegetable oil and hydrogenated vegetable oil, and biodiesel, and we have bioethanol. So we can see here, we're very much an UCO-dominated biofuel market. Category 1 tallow, and then an array of other feedstocks. We can see the lower, or the smaller markets. The bio-CNG market is relatively new in Ireland. We do have an indigenous producer producing it from brown grease, food wastes, animal manure, and belly grass, which is a category 2 tallow. But UCO makes up some of bio-LPG. It comes into CHVO, and it's also used to produce biodiesel. Unfortunately, there's nothing here on algae yet. It hasn't been placed on the market in Ireland as of yet. And you may think that's quite an array of biofuel feedstocks, but just to take the equivalent UK feedstock palette, you can see here there's huge amounts of different feedstocks, some of them very unusual. Again, there's no algae in the UK that's coming onto the market, but we can see that there is everything in between, such as waste slurry from the distillation of grains. We have poultry feather acid oil. There are some very unusual feedstocks that are used to produce biofuels. So what I would say is that there's great hope, or there's great an awful lot of invention in the biofuel market to use particularly waste-based feedstocks that don't impinge on land use. So again, you'll see here the extreme prevalence of UCO in the UK market, and that's a common theme throughout Europe. Maybe not to the extent that it is in the UK and Ireland, but UCO is very much relied upon for biofuel production in the EU. So we talked a bit about sustainability, and Conal has referred to that already. So what exactly does it mean to be sustainable? And in summary, we have three fundamental criteria. We have our greenhouse gas savings criteria, which is the one that most people are familiar with. We also have biodiversity. So you can't start growing biofuels or producing biofuels in lands that are designated as specially protected area, SPA, or special areas of conservation. You can't also grow biofuel on land that was obtained from land that was with high carbon stock. So if it's primary forests or undrained peatland, you can't use that land to produce wheat or corn or start growing any sort of biofuel feedstock. So these are the tenets of what it means to be sustainable. And if these sustainability criteria are not satisfied, then the biofuel cannot be counted as a bona fide biofuel. Also, another important note is around greenhouse gas intensity or carbon savings. And this is one that probably gets the most focus, because that's the driver behind a lot of our legislation to reduce greenhouse gas emissions. So when we look at sustainability of biofuels, we're talking about life cycle greenhouse gas emissions. So it's the greenhouse gas emissions per unit of energy over the life cycle of the production of that biofuel or fossil fuel. And it depends on the fuel type, be it diesel, gasoline, bioethanol, etc., what feedstock there is, and also on the fuel chain, so the processing steps that are used. Where is it transported from? How far is it transported? And we're just giving a brief example just to show how this calculation is carried out. Now, we have a carbon calculator that's available online that allows you to build biofuel supply chains to examine what is the life cycle carbon intensity of a biofuel. And this is an example of one. And it's a biofuel plant that takes some sort of rapeseed or palm oil or something like that. And it breaks down all the elements of the supply chain that consume energy, or other chemicals that could have greenhouse gas emissions associated with them. So we can see here we have crop production, then we have some drying and storage, some transportation, then you have biofuel plant production modules that also go ahead that use energy and emit greenhouse gases. You have transportation again and storage. In this particular supply chain, and what's common to all supply chains, is the production of a crop itself takes an awful lot of energy and chemical inputs that release an awful lot of greenhouse gas emissions. The second largest contributor to the makeup of the greenhouse gas emissions are the energy consumed in the biofuel production plant itself. And in fact, the transportation step, of which there are 3 in this particular module, does not typically consume an awful lot of energy, and therefore does not typically emit an awful lot of greenhouse gas emissions. So that has contributed significantly to the global market for bioliquids and biofuels in particular, because the transportation step does not typically take up an awful lot of energy to move vast quantities of bioenergy around the world. I'm talking about biofuels now. If you're talking about biomass, where it's heavier, less energy dense, this becomes a different story. But for bioliquids and biofuels, that's typically the case. So it's important to take away that it's life cycle greenhouse gas emissions we're talking about. And in the case of biofuels, when you look at the life cycle, when you can consume the fuel or when you burn it, that then is considered to be zero emissions at the point of combustion. So that's when typically, when national inventories are looked at for Ireland and other countries, they look at what are our greenhouse gas emissions. Atmospheric biofuels are counted as zero on a tailpipe basis. On a life cycle basis, shouldn't be forgotten that upstream emissions exist, and depending on the biofuel production process, they can actually be very, very high. So at a glance, the BOS has been the primary mechanism for meeting our RED, and it will be our primary mechanism for meeting RED 2 targets. While electric vehicles get an awful lot of press and focus, and rightly so, for future greenhouse gas emission reductions, it has been biofuels that have contributed by far the most significant contribution towards Ireland's reaching its 10% renewable energy target in transport. And it will continue to do so for the majority of this decade until we get significant proportions of electric vehicles on the market. In terms of, just to give you a flavor for volumes, now I'm sure in China the volumes are many multiples of these, but they might seem very small. But in Ireland we put approximately 4 billion litres of fossil fuel on the market and about 250 million litres of biofuel. So it's not an insignificant quantity. As I talked about before, it's a certificate-based system. So in Ireland, you get one certificate per litre, or in the case of waste or residues, you get 2 certificates per litre. So even though Ireland's headline figure will be 10% renewable energy, in fact, we're more likely to be around, by actual volume, around 6%, because a lot of that biofuel has been double counted. The main, and we've already talked about the main feedstocks that have been supplied into the biofuel market in Ireland. And where is it coming from? The majority of our biofuel feedstocks come from Ireland, but an awful lot of it comes from Asia, specifically China, which is a large contributor of UCO-derived biodiesel into Ireland, and of course throughout the EU as well. But we also get biofuels from North America, South America, small quantities from Africa, and as far away as New Zealand and Australia. So as I said, it's a global commodity that's traded on a global scale. So to look at where we're going into the future, we'll have RED 2, which will set more ambitious blending requirements on biofuels for the next decade. We're currently at a 10% obligation. We're moving to a 14% obligation, but we're also bringing in other caps and limits and sub-targets. And importantly, from perspective of where algae is seen, it'll be part of this advanced biofuel section down the bottom here. And there will be specific sub-targets in 2030 of 3.5% of final energy use in transport will have to be met with advanced biofuels. And I'll talk about that again in a second. There are other multipliers then involved in reaching these targets. So for EVs, you have a 4-time multiplier. For renewable electricity and rail, 1.5. For maritime, 1.2. And aviation, 1.2. And then your advanced biofuels are all double counted. So this is where the incentive comes in for advanced biofuels. Okay, so when we say advanced biofuels, what are they? What exactly are advanced biofuels? This here, you may have heard the term or may not, but it's a term that's used an awful lot in biofuel circles, and it's the Annex 9 list from RED 2. And it defines what advanced biofuels are. So this is part A. So anything here listed from A to Q are considered, if they're produced from these feedstocks, they're considered to be advanced biofuels and meet the advanced biofuel target. So number 1 here on the list, as you can see, is algae if cultivated on land, in ponds, or photobioreactors. Some of these are very straightforward. If it's produced from straw, tall oil pitch, bagasse, nutshells, these are well defined. There are, however, some of these that are not quite as well or tightly defined. For example, biomass fraction of industrial waste not fit for use in the food or food chain. We've had some problems with categorizing feedstocks that may fit into this definition because it can be somewhat subjective. So what does it mean to be not fit for use in a food or feed chain? And that can differ between countries. So some of these are straightforward. Algae, for example, is straightforward. Other ones are not as straightforward. So there will be some decision making as to what feedstocks fit into some of these categories. And to give you a flavor of what has been put on the market thus far in Europe, this is a breakdown of 2020 data broken down by the Annex 9 lists, Annex 9 definitions across the bottom. And this is based in terajoules. So the largest proportion of advanced biofuel feedstocks placed on the market thus far has been this category D, which is biomass fractions of industrial waste. And again, to give a context for what does 30,000 terajoules mean, in Ireland, Ireland's gasoline consumption is around 25,000 terajoules. So this is not too far off. This bar here is Ireland's total consumption of gasoline is more or less how much was put on the market in terms of advanced biofuels in 2020. But we can see, unfortunately for you guys at the moment, the algae side of things is there's a zero quantity been put on the market thus far. That's along with some other ones as well. So it's dominated thus far by biomanufacturing, industrial waste, and this one here, palm oil mill effluent, or empty palm bunches, which is a waste from the palm oil production industry. And again, to put this in some context, the yellow bar here is the total Annex 9, so it's the sum of all of these values across here, up around 60,000 terajoules. But in the EU in total, the total quantity of UCO-derived biodiesel, it's about 4 billion litres, is up around 140,000 terajoules. So that's how relatively small an industry the Annex 9 Part A advanced biofuel portion is compared to one of the largest biofuel feedstocks, which is the UCO-derived one. And then to meet the advanced biofuel target in 2030, which is the 3.5% advanced biofuel target, this is how much advanced biofuels approximately we're looking at, 250 petajoules, which is a significant increase on the current quantity of advanced biofuels put on the market. So the message here I'm saying is that really the demand for these types of biofuels will be increasing, and they will be increasing significantly in the coming years. So the research you're doing on algae going into any form of end use, be it transport or anything else, it looks to us, based on the policy that's being put out there, that there will be a significant demand for these types of biofuels in the future, as we try to move away from crop-based biofuels, which take up land use and divert and cause indirect land use and indirect greenhouse gas emissions. So again, as Conal referred to as well, there's also RED 3, which is coming down the line, and it's going to replace the blending obligation with a carbon intensity reduction target of 13%, which is an increase in the level of ambition. And importantly for you guys, that the advanced biofuel target remains, but there will also be this RFINBO sub-target, which is an important and an interesting one. So it's renewable fuels of non-biological origin. So these are things such as hydrogen produced from electrolysis, for example. And then also another market that will be opening up, it's in its infancy at the moment, is obligations on international aviation fuel. So there will be a blending mandate brought in to increase the penetration of sustainable aviation fuel in the aviation sector. So that will also increase the demand levels for biofuels, and particularly advanced biofuels, as we move into as we progress through this decade and move in towards 2050. So I think that brings me to the end. I trust I'm not too far off time, but thanks very much for your attention. And if you have any questions now, I'd be happy to take them.
Yeah, thanks, Shane. A lot of information there, very interesting. Shane, just because time limits, I just one quick question. So Professor Dagmar Stenger asked you a question. She asked you that, regarding advanced biofuels, why do algae have to be produced in ponds on land? So no marine open shore cultivation? What is the reason for that?
It's a very good question. And I did think of that question when I was pulling this together, but I'm afraid I don't have an answer. That is the definition that's provided in the Renewable Energy Directive Part 2. What I would say is that those definitions and what's contained in Annex 9 Part A can be added to, so it can be supplemented. So perhaps it's a question that can be taken up with the European Commission, who are the founders of that Annex 9 Part A. So I'm sorry I can't answer that question. It does seem odd, but I'm afraid that's the definitions in which we work at the moment.
Okay, thanks, Shane. Thanks. Yeah. Okay, so we'll move to the next presentation. So next presentation will be given by Professor Theodoropoulos. Professor Theodoropoulos will talk about algae biomass as a biorefinery platform for biobutanol and biodiesel production. Professor Doropoulos is Professor of Chemical and Biochemical System Engineering at the University of Manchester. So he leads a leading group in the area of industrial biotechnology and multi-scale process dynamics of biochemical system. So before the presentation, I just tell you guys that exciting news that we have more than 100 participants on Zoom, but also I just checked the live stream channel in the China site because I couldn't find the number for YouTube live channel. Now there are more than 300 participants there, so it's very good. A lot of people are interested in the presentations. Okay, please, Professor Theodoropoulos. So the floor is yours.
Thank you very much. Thank you for the kind invitation. Good morning, everyone. So today, let me share my screen first.
Yeah, please.
I think I can. Let's see. Yeah. And then let me go into presentation mode. Can everybody see? I hope, yeah? And here, right. So, like I said, today, I'm going to talk about our research at the University of Manchester of combining experimental and modeling technologies to use microalgae as a biorefinery platform. Well, here for biofuels, but not only. We try to do a number of things. And this is a picture of the central building of the University of Manchester on a sunny day, as we have today, which is not very common. So I'll give you a brief outline of the talk. I'll start with a short introduction on microalgae biorefineries. Then I'll talk a little bit on how we integrate, as I said, models and experiments. Talk about the importance and type of models and model building process, and all of that is to optimize the production of microalgae. And then, if time permits, I'll talk about one or two particular things we've done. One is nutrient-enhanced batch cultivation and optimized for biobutanol and biodiesel production, as in the title. And the other one is an even more enhanced mode of cultivation, which is fed batch. I'll very briefly mention our scale-up efforts because that belongs to a totally different presentation and conclude. Okay, so since you are here, I think you all know that microalgae are a very potentially efficient microbial factory, a full production system, right? They are photosynthetic microorganisms. They take in sunlight and then nutrients, clearly water, and then carbon, either as CO2 or as organic direct carbon source. And by consuming all of those, they grow appropriately, and within them grow, within the cells that grow a number of compartments, which is starch compartment, a lipid compartment, which has also an important subcompartment that comprises a number of pigments, and then proteins, vitamins, nucleic acids, etc. And all these compartments are very useful for products. So from starch, we can produce biobutanol and bioethanol for biofuels, for example. From the lipids, we can produce biodiesel directly or even aviation fuel, as the previous speaker mentioned before. The pigments are very important because there's a number of high-value products like nutraceuticals, food products, and cosmetics that we can produce. And then from proteins, we can get pharmaceuticals, bio-oil, recombinant proteins, etc. Even after we use all these important compartments, the rest of the cell can be used, for example, for the production of methane and hydrogen from anaerobic digestion, aquaculture, feed or animal feed, or for soil conditioner, bioremediation, and everything. Basically, we can use every part of the cell to produce something useful. However, we know, and I think also that was kind of implied in the previous talk, that it's not profitable to grow microalgae for one single application. So this biorefinery type of approach make sense. And this is a conceptual picture of a microalgae-based biorefinery. We start by selecting an appropriate strain, of course. Then we cultivate using sun, nutrients, feeds, different feed, for example, organic carbon, right? Then harvest and drying is the next step. We can pre-treat the biomass, for example, through hydrolysis, but then there is a very important extraction step, which can be either, again, through hydrolysis to extract sugars, or through solvents to extract lipids, or through supercritical fluids or other green solvents, which is also other work we are doing. And then after the extraction comes the conversion step. So sugars can be fermented, again, for biobutanol or bioethanol. Lipids can be transesterified to produce biodiesel, or they can be purified for the pigments, such as astaxanthin, beta-carotene, lutein, etc. And then what's left can be hydrothermally liquefied to produce bio-oil or biochar, or pyrolyzed for that matter, or combusted to produce electricity or animal feed. And then I've missed here an important component, which is the protein part, which is another important set of products. Okay, so here's all the potential range of products that we can use from microalgae. But in the center of this, for all of this to be viable, economically viable, is the cultivation. Okay, so we want to control and optimize the outcome of microalgae cultivation, and that's what I'm going to focus on today. So how do we do that? We do that through, in our lab, through integrated system approach for bioprocess optimization, which is through the development of bioprocesses from large scale to pilot scale, right? And we optimize them by applying biochemical engineering principles. So how does it work? We start, of course, with selecting appropriate strains through screening and biotraining. We do a number of experiments at laboratory scale for cellular growth and production, and then we model. We develop models at different scales, and we use them for model-based design, scale-up, optimization, and control. And you see here a couple of, all the scales that we have. So from the lab scale to photobioreactor scale to open pond scales of 500 liters each. Right. So as I said, we develop models. There are different types and scales of models, and that's important, right? So we start from the macroscopic scale, where the biomass is kind of a gray box. We don't need to know exactly what its cell does. What we are interested in is what kind of inputs we put in, and we want to predict what kind of outputs we get. That's very important also. And these are actually the kind of models I'm going to talk today. So I'm going to talk about macroscopic modeling, sorry. And then we go to the next level down, which is mesoscopic models, where again, we're interested in the inputs and outputs, but then the biomass we address at the cell level. So we're interested in the number and concentrations of different cells and their compartments. And then you have the almighty microscopic models, where we are looking at what happens inside the cells, the metabolism in each and every cell, right? And then the production processes too. And of course, these are very large and very tedious models. And of course, we need to know a lot about the mechanisms, the reactions, and the reaction rates and everything else. Okay. But like I said, today, I'm going to focus on macroscopic models. Okay, so right. So how do we develop these models? The process is pretty much this. On previous knowledge, right, we design a number of experiments, normally at laboratory or bench scale, right? And then we process the data, And through the data and experience, of course, we establish a model structure. The goal is to get the input and output relationships that are comparable and agree well with the experiments through a number of kinetic equations. And then the cares and blessing of this kind of models is they come with a large number of parameters. Then these parameters need to be fitted to experiments, but that's not enough. That's far from being enough. There are two important steps after fitting: the sensitivity analysis to make sure that all the parameters we have are meaningful, and then there's identifiability analysis to see how close the parameters we have are to the kind of true parameters that a good, reliable model would have. That's not an easy step, right? But after that comes model validation. So we want to assess the model predictive capability through another set of experiments. And if that works, okay, we're okay. But if that doesn't, we need to go around this iteratively until we're happy. And then we have a model that we can trust and rely on, and we can use it for system tasks, so we can exploit it as an optimization or a control tool or both. Okay, so let's see what we do with those, right? One is we take a batch cultivation system and we use this kind of integrated approach to maximize starch and lipid formation. And as you know, from starches, then from starch we produce biobutanol, and from lipids we produce biodiesel. So the main idea here is that nutrient availability affects very much both growth and growth of the starch and lipid compartments in the cells. Right? So too much nutrient availability will give you good growth, but, and this is a well-known fact, but not enough starch and lipids. If you deplete, if you starve the system from nutrients, you get good growth in the starch and lipid compartments, but not enough cell growth. So it's a trade-off here, and we have to exploit it. Mixotrophic growth, so if we put a carbon source, helps to also boost the cell growth, but that's not enough. There's too many possibilities, and that's where a model becomes helpful. So in this particular example, which was published recently in Biotechnology and Biofuels, we use Chlamydomonas reinhardti as our microalgae strain of choice, not necessarily because it's the best producer. Actually, we're working with much better producers, but because we know a lot about the strain, the metabolism, and we can develop trustworthy models, right? We have in the beginning a standard growth medium TAP, right? Triacetate phosphate that gives you your carbon source, phosphorus and nitrogen nutrients, well-defined conditions here. And then we can supplement nutrient, phosphorus and carbon through acetic acid in this case. Okay, so and then we run a number of experiments at very carefully controlled conditions in the laboratory scale, and we measure biomass, starch, oil production, total nitrogen, total phosphorus, and then acetic acid consumption. Okay, so the model we develop is a compartmental one. It's a macroscopic compartmental model, and then we have a number of compartments in it. We have total biomass, then we have a starch and a lipid compartment, and they come and interact from the active biomass part of the total biomass. Of course, we have all the interesting inputs: acetate, light, nitrogen, and phosphorus. And then the nutrient availability, the nitrogen, phosphorus, come through some quota concept here. So we have nitrogen quota and phosphorus quota, which is again a measure of the availability of these nutrients in the cell. And then there are essentially reactions between all these compartments. And the model we develop looks like this. It's set of equations, which are ordinary differential equations, and they give you the evolution of total biomass, nitrogen consumption, nitrogen and phosphorus quota evolution, phosphorus consumption, acetate consumption, starch and lipids production, and then how active biomass is evolving. These specific growth rates here are important because they contain pretty much all the phenomena taking place, and then each of them is a factor of all the inputs of the acetate, of the light, of the nitrogen, phosphorus quota, and everything else. So, and this is how the specific growth rates look like. So, the specific growth rate for biomass has a heterotrophic term, which is the carbon term, and a phototrophic rate, which is the light term. Here, the nitrogen uptake depends on nitrogen, of course, but also depends on acetate and on phosphorus quota, and the phosphorus uptake depends on phosphorus, but also nitrogen quota. So we can see all the interrelations between the different inputs are captured. There are terms that give you inhibition. If you have too much of something, basically it has the opposite effect, right? We have luxury consumption, and we have even a degradation term. So it's a pretty complex macroscopic model. And then, like I said, we go through an intensive fitting process. We use global optimization to find the global optima of the parameters that will fit the data, but that's not enough. We undergo sensitivity and identifiability analysis, and we go through a number of iterations to make sure that the model with its parameters works and has predicted capabilities that can be later used for optimization. So how well does the model work? It works very well, actually. And this is just one set of predictions at conditions different than the ones, of course, used for fitting. And it works very well for different conditions of so high and low nitrogen, high and low phosphorus, high and low acetate, and everything else. So it captures the whole range of handles we have in the system. And you see the agreement is very good for all variables and for all cases. So we have a model that we can trust, and again, that's just one picture. There's more. I mean, we've done an extensive validation study there. So what we can do is we can use the model to optimize the system. So here, it's an optimization, but this is a parametric analysis. So we have these ternary diagrams where we have nitrogen, phosphorus, and acetate in all. And we want to optimize different things. Here, we want to optimize biomass. Okay, so what's the combination of these three inputs to get maximum biomass? So what's the combination to get maximum lipids? Or what's the combination to get maximum starch? The take home from this, and it's very interesting, is that the different objectives will give you different inputs. So if you want to optimize different things, you have to operate differently. And that's very interesting and very important. That's a take home from that. Right? So here, this is one of the graphs that made us very happy because of the dots here, right? So the bars are the optima calculated by the model. After the model, we ran the optimal cases with the inputs that the model told us, and they are bang on the predictions. So that made us very happy. The other thing that made us very happy is that, if you optimize starch, for example, you go 270% above the base case. And if you optimize lipids, you go 74% above the base case. So you can really make a difference by optimizing the system. Okay. Right. And then what we can do is we can take the starch and the lipids and make, and this is just a base case study. It's not that's a feasibility study, really. So we make biobutanol by ABE fermentation with Clostridium acetobutylicum from the starch that we get from the optimized cases. The thing there is we do two things. A, we take the biomass as it is and we ferment it, or we hydrolyze it to release the sugars. So we do both things here. And then we transesterify again the biomass, either before we extract the starch or after we extract the starch. So we do both studies here, and we produce biodiesel. So what you can see here is that the hydrolyzed biomass is red, the microalgal biomass is green. If you hydrolyze through fermentation, you get better growth because it's more ready sugars. It makes sense. However, the biobutanol you get is pretty much comparable if you hydrolyze or if you don't hydrolyze. So that's an important, again, an interesting result we didn't expect. The transesterification results are here. So this is the biomass, hydrolyzed biomass, and fermented biomass, right? What is interesting to see here, and again, need to be careful of my time here, is this, that the hydrolyzed biomass, right, will give you much better yield of biodiesel. So although we hydrolyze to get more sugar for the fermentation, in addition, we can get better biodiesel yield. Okay. Again, there's a number of things we can do here. Like I said, we can mix and match the steps. We can take the biomass and ferment it and then transesterify the fermented biomass, or we can hydrolyze and then we can transesterify again the hydrolyzed biomass, and there's different combinations we can do here and in the pre-treatment steps. How much time do I have? Cannot hear you.
You almost end of your time.
Okay,
no.
So I'll give me 3 to 4 minutes. Yeah.
Maybe just 1 minute. Okay.
1 minute. Okay. So then I'm gonna skip through this. But what I want to say is, on top of doing this, we can optimize even more by adding pulses of the organic carbon, right? So for that, we've tried different experiments. We've developed the model a bit more to capture this pulse behavior. But the idea, I'll just show you this, is that if you put intermittent pulses at different times, 156 hours, 260 hours, 444 hours, you can increase starch even more, up to 670%, and lipids even more, 250%. So that's an important one, right? I'm skipping it for time limitations, but I have to say these results were very, very recently, were very recently published in Sustainable Energy and Fuel, so you're welcome to have a look at this. Okay, so I'll just say that these models were based on lab scale results, but then we're using the optimization to scale up on our photobioreactors and our 500-liter open raiseway ponds, right? And actually with different number of strains. Again, that's a different talk. I'll quickly conclude. I hope I convinced you that, but since you're here, I think you're already convinced that microalgae biorefineries can offer viable, sustainable, high-value added products, and you can optimize those much more efficiently if you integrate experiments and models at different scales. Okay. The future is mixotrophic and fed batch. In my view, there are particular challenges, of course, especially if we talk about biofuels. How to get to the large volumes required is very important, right? There is scope for different type of modeling too, but again, the main target is how to boost production and productivity. Okay. I'll put the acknowledgements page here. These are my collaborators that did pretty much all the work that I presented. Well, John is also a colleague in Manchester. He's a biologist. And I'd like to just to mention that the Enhanced Microalgae project is an Interreg EU project that is currently running and been running for the last 4 years and has been funding a lot of this work. Thank you very much.
Yes, very much. Constantino, thank you for your nice presentation. I'm sorry because the time limit just, but I know you have more slides you want to share. I'm sorry for this, but next time we organize another one. So thanks. Yeah. So it's okay. I see there are no questions from the participants, but I have just one quick question. I see you use the acetic acid in your model. Your acetic acid in your model. You don't include carbon dioxide. So does this mean that your microalgae is not autotrophic microalgae or is just heterotrophic microalgae?
So this is mixotrophic. So the algae, there's a light source also there. So the algae feeds from the photosynthesizers, of course, but also uses organic carbon to boost productivity. So it's a fully mixotrophic growth.
Okay, thanks. Yeah, very much. Thanks. Okay. Yeah, so thanks. Okay, so we move to our next presentation. So our next presentation will be given by Dr. Jonathan Wagner from the Loughborough University in UK. So he will talk about the integration of anaerobic digestion with the algae assisted biogas purification and hydrothermal carbonization of digestate. So I have quick introduction of Dr. Wagner. So Dr. Wagner is a senior lecturer in chemical engineering at Loughborough University in UK. So his research focused on the production of sustainable chemicals and fuels from biomass and waste. So currently he's a program leader for the 4.3 million sterling UKRI in the Disciplinary Center for Circular Chemical Economy. So yeah, very much. Please, Dr. Wagner.
Right, okay, I hope you can see my screen.
Yes.
And you can hear me. Okay, thank you very much for inviting me today. It's a pleasure to present the results from the study on using algae for biogas purification. Just very quickly about a microgroup in general, it's about trying to develop circular fuels and chemicals using biomass and waste. And as already mentioned, I'm part of a circular center for chemical circular economy, and we're looking at different routes to do that. As you will be aware, there's many different technologies to convert biomass and also waste into fuels and chemicals. But each of these technologies on their own have some advantages and disadvantages, and most of them only use part of a material. So to make the process more efficient, it's actually quite important to try and combine different complementary technologies. So for example, we can use hydrothermal liquefaction to use some of the biomass fractions, and then we can use complementary technologies such as anaerobic digestion to use as much of the carbon and the energy that's contained in the biomass as possible. And to do that, we need to look at each individual technology, but we actually need to combine them in a whole system and optimize the system as a whole, where actually some of the individual steps might not be at the optimal point, but the system overall performs better. In my group, we're looking at combining different approaches. So we use thermochemical processes, particularly hydrothermal processes, and then we combine them with both biological and catalytic processes to develop whole systems. But for the rest of the talk, I want to talk about one specific project which we did around 2020, and that was to develop a algae-based biomethane purification process, where we're using biogas from anaerobic digestion and algae to separate the CO2 to produce pure biomethane fuel. The project was co-led by my colleague, Dr. Tanya Radu, and most of the work was done by the postdoc, Dr. Uttam Roy, and the project was funded by Department for Transport and also Supergen Bioenergy. So just a very quick background about anaerobic digestion, and we've already heard about that earlier. It's a very diverse process that can use a wide range of different biomass wastes and convert them into biogas. And this process has a lot of advantages because biogas can be easily separated. The process also produces a digestate, which could be used as a land fertilizer. And it's quite a simple process. At the moment, there's over 670 anaerobic digestion plants in the UK already. So it's a well-established renewable energy technology. The biogas can then either be burned for electricity and heat generation, or it could be purified as a renewable biofuel. However, there are some current challenges. The first one is around the purification of a biogas itself. Biomethane is worth quite a lot more than the gas as a whole. Despite that, only 10% of current plants actually purify the biomethane. And the reason for that is the high infrastructure costs of existing processes, and also what to do with the recovered CO2 if we're using physical separation processes. The second challenge is the use of a digestate. I've already mentioned that it could be used as a natural fertilizer. However, it contains also high water content, and that makes it difficult to transport. And within the surroundings of the anaerobic digestion facility, the land capacity is often not enough to deal with ammonia emissions and other potential contamination. So to address that, one way is to replace conventional physical separation processes by using algae. The biomethane value has approximately 70% higher value than the equivalent amount of electricity. And the second advantage is that we're using the CO2 rather than having to deal with it separately. The algae actually uses it for growth. And there's a potential to then recycle the algae back to the digester to increase overall biogas production. Secondly, we can use the digestate as a feed for hydrothermal carbonization, and then use the resulting biochar as a potential for carbon storage, and that can then further reduce our carbon emissions from the overall process. Or we can even have a net zero process or a net negative process where we're selling the carbon credits from the biochar. So this then led us to develop a new process. So we are taking a conventional anaerobic digestion system producing biogas and digestate. We can't use algae directly for biogas purification. Algae takes up the CO2, but it also releases oxygen. And the last thing we want is a mixture of methane and oxygen. So we adopted a two-step process. In the first process, we're using a carbonate solution to absorb the CO2, and that produces bicarbonate. And then that bicarbonate solution can be fed into the algae culture, who are then reversing that reaction to regenerate our carbonate absorbent, whilst taking the excess CO2 for algae growth. On the second part of the process, we're taking the digestate, we're hydrothermally carbonizing it to produce our hydrochar. However, that also allows us to extract residual nutrients from the digestate, which we can then recycle back to the algae cultivation to reduce our nutrient requirements for the process. Now, the first step was to actually identify a suitable algae that could do the carbonate regeneration. And to do that, we looked at existing halophilic microalgae and cyanobacteria and screened them for the tolerance to different levels of bicarbonate. And as you can see, the most promising strains based on this initial screening were strains from Dunialela tetralecta. It's a already highly commercialized strain used for beta-carotene production. And that could grow at concentrations of at least 40 grams per liter of bicarbonate. So then we took that first strain and we screened it up to the maximum bicarbonate concentration, which is a solubility limit in water of 90 grams per liter. And we could see that we got good growth even at very high bicarbonate concentrations, with the best growth obtained around 20 and 40 grams per liter. At the very low concentration, the growth is actually carbon limited due to the cultures that we used. We didn't do any CO2 bubbling. That's why the growth rates are very low. But definitely at 20 and 40 grams, we got very high growth rates. But of course, we wanted the microalgae to regenerate our carbonate, so we needed to monitor the fate of bicarbonate over the course of a cultivation cycle and ensure that we're actually producing carbonate. Unfortunately, this is exactly what happened, and the carbonate yield was almost exactly 50% of the converted bicarbonate, which is as we expected. We can then plot the CO2 absorption capacity of the spent algae medium against time. And we can see as we're increasing the initial bicarbonate concentration, we're also then increasing the amount of carbonate that is generated. So generally, the absorption capacity goes up with increasing bicarbonate concentration, except for the very high concentration of 90 grams per liter, where some of the carbonate product precipitated out in the solution. But of course, we're also interested to see what we're actually producing. So we monitored, so 50% of the bicarbonate went to carbonate. Some of that went to algae, but as we increased the bicarbonate concentration above 20 grams per liter, more of that carbon was actually released or lost through the system. So we assume that was carbon dioxide, and the amount of algae yield or relative algae yield was reduced. So this is both a positive and a negative result. Firstly, we obviously want to produce algae as a byproduct. So the efficiency of converting CO2 to algae is reduced at high bicarbonate concentration. But at the same time, it tells us that actually the capacity of the algae culture to regenerate the carbonate absorbent is higher than the algae growth. So even if we operated under non-optimal conditions, for example, during winter with limited sunlight, the system could still work without any additional optimization. The next step was then to look at the CO2 absorption. So here we used a batch system to monitor the conversion of carbonate into bicarbonate. And again, we can plot the conversion of carbonate into bicarbonate over time. We can then look at using different biogas flow rates, and we can see that at flow rates above 45 milliliter per minute, the uptake became limited by the solution. And at the same time, increasing that flow rate above 45 milliliter per minute means we don't increase the uptake any further, so our outlet purity reduces. But what you can see from a single step, which a batch system represents, we can go from about 60% biomethane purity to 85% biomethane purity. So the system can be converted into a continuous system and can achieve outlet requirements. But of course, what we want to do is demonstrate the system that it can work as a closed system. So now we cultivated the algae culture in the spent absorbent, and we saw similar uptake in the or growth in the spent absorbent as we saw in the fresh control medium. However, the regeneration of the carbonate was slightly slower than it was in the fresh solution. And then finally, we can take that regenerated medium to recycle it back to the CO2 absorber. And we can see that the initial uptake over the first 150 minutes is the same, but then it starts to drop off compared to the fresh medium because we have less carbonate in the solution. Now, we wanted to look at the overall carbon balance of the system. We wanted to produce a system which is carbon neutral or even carbon negative. So we used the anaerobic digestion of sewage sludge as a case study. And here we're using a fed batch digester, which we're using in our lab to get the total biogas production and also the composition of methane and CO2 in the biogas. And then combining all the data from our own study based on a bicarbonate concentration of 32 grams per liter and using HTC yields from literature, we managed to do an overall carbon balance across the system, which shows that around a third of the total carbon ends up in our final biomethane product. About a quarter ends up in the biochar, and this could potentially be used to offset the system emissions. We do have quite a lot of losses in the system, but this is we mostly attribute this to the batch nature of the processes. So if we are managing to integrate it into continuous process, which is the next step we want to do, we're expecting that these losses can reduce substantially. And of course, we're also producing around 8% of algae, again, under currently non-optimized conditions. So the next part was to actually then look at the HTC of a digestate. So hydrothermal carbonization produces both a hydrochar and an aqueous phase, as well as some carbon dioxide. Using the different HTC temperatures, we get a biochar yield of around 80% at the lowest temperature of 200 degrees. But we can see that we still get some fractionation into the aqueous phase. So we can then look at the carbon balance, which looks quite similar to the overall mass balance, but we are interested in recovering the nutrients. So if we look at nitrogen, we can see that around half the nitrogen ends up in the solid and half of the nitrogen goes into the aqueous phase, and most of the nitrogen is in the form of ammonia rather than nitrate. Next, we wanted to look at the fate of the metals, particularly the heavy metals in the digestate. Consistent with previous studies, most of these heavy metals go into the solid phase, which is where we wanted. So we reduce the volume of these metals and we can dispose of them safely. There's some exceptions at the back, like cadmium and bismuth, but those concentrations were so low that the concentrations in the aqueous phase were still well below the toxic levels. And then we also looked at the recovery of the nutrients, which we need in our synthetic medium. And we compared the concentration in the aqueous phase to the concentration in the medium. We saw that most of the nutrients are in 10 to 50-fold excess to what we need. So that tells us that we want to dilute our aqueous phase before we use them for algae cultivation. Now we then use that HCC water in low concentrations added to the existing medium to look for potential inhibition. And we saw that for the lowest temperature of 200 degrees, we could grow at concentrations up to 2% and with very little inhibition. But when we went to the very high HCC temperature of 240 degrees or the very high concentration of 3%, the algae growth was inhibited. And that is even more clearly shown in the chlorophyll content of the strains, which indicates the health of the species. Again, the strains did not look very healthy at high HCC temperatures or high concentrations above 3%. And this is just the summary of our growth parameters. So finally, we obviously still wanted to look at the potential at our carbon balance after the conversion. So for all the conditions, we got pretty much 50% carbonate recovery. But obviously the algae biomass yields were significantly reduced for the inhibited conditions. What is interesting is that we got carbonate recovery even for those two cultures, which did not grow very well. And that can be explained by looking at the culture pH, which goes up over time, and the carbonate bicarbonate ratio is equilibrium based. So even if those cultures are not growing, we can still, the pH still went up, and that can explain why we're still regenerating the carbonate. But of course, that would not be a long-term sustainable system. So in conclusion of this study, we wanted to develop a proof of concept, and we were very happy to see that the algae indeed were able to reversibly convert the spent carbonate solution, the bicarbonate, back into carbonate. And the preliminary carbon balance suggests that the system has a high degree of carbon utilization. And second, we also saw that HTC has the potential to recover sufficient nutrients to maintain the system. There are still some questions around inhibition, and we need to do further studies into that. But generally, the overall algae productivity at low concentrations was even higher than the algae productivity without added HTC water. So going forward, we are hoping we've applied to larger grant to take this work forward. So we're hoping to hear the outcomes over the next few months, and that would be really looking at demonstrating the system in a continuous way, looking at the composition of the algae in more detail, and really identifying the best overall outputs for the system. So I hope I'm not too far over time. Thank you very much for listening.
Yeah, very much, Jonathan. So very good time control. Thanks. So I have two questions actually. One quick question is that I see you use the hydrothermal, treatment, treated digestate to grow microalgae. So you have considered, their inhibition, possible inhibition from, metals and trace nutrients. Have you ever considered whether, when you do hydrothermal treatment, whether there's some generation of toxic organic materials that will also inhibit algae growth?
Yeah, absolutely. So I think what we've shown is that the problem is not the heavy metals, and we're recovering most of them. So the inhibition almost certainly comes from the production of organic compounds. And that is also consistent with those compound generation increases with higher temperatures. We haven't done a detailed analysis of the composition of the aqueous phase. So there's two things we can do. We can try and minimize the production during HTC, or we can try and introduce an additional treatment process. We can add an absorbent or adsorbent to the culture to reduce the inhibitor concentration. Or, of course, we can try and increase the tolerance of the algae strain to the inhibitor. As I said, these are the kind of things we're hoping to do in our follow-on studies.
Okay, thanks. So another question from the audience to say, will high carbonate concentration inhibit algae growth?
So it's nothing that we've seen. We've gone to the maximum bicarbonate concentration, and we saw slightly lower growth, but that's probably within the error of the experiment. So after 7 days, the growth was slightly reduced. After 11 days, we got very similar growth curves. So based on that, I don't expect that the high bicarbonate concentration inhibits algae growth. We've done some studies where we actually added, we used a mixture of carbonate and bicarbonate, and we saw that actually improves the cultivation because it acts as a buffer solution. And that means we could reduce the amount of tris buffer, which is unnecessary expense. But yes, I don't expect that that's a major issue.
Okay, yeah, very much. Yeah, thanks, Jonathan. So, okay, thanks. So we move to our next speaker. But Jonathan, don't go away, because you will also join there panel discussion later. Yeah. Also, our next presentation will be given by Professor Arur Manus from Valladolid University, Spain. So he will talk about Microalgae for spontaneous biogas upgrading and centric treatment. So Professor Manus is experienced in biological gas treatment, biogas upgrading, bioplastic valorization, and wastewater treatment. So he's an expert in algae bacterial photo bioreactors. Okay, yeah, please, Roar. So the floor is yours.
Okay, thank you very much for this presentation, and thank you very much for this kind invitation to be part of the workshop. Okay, we'll present today some of the work we have done in this in the topic of photosynthetic biogas upgrading, which is a technology that we have been working since 2012. Okay, so just a brief summary of the biogas market, the biogas production in the world. You can see clearly how the biogas in the last decade has been gradually increasing in all regions in the world. Europe continues being the region in the world with the largest potential, although Asia is rapidly developing capabilities in this topic. In Europe, the number of biogas plants increased rapidly from 2009, around 6,500 plants, up to 2014 with more than around 70,000. And from 2014 onwards, there was a gradual, a slow increase in the number of biogas plants. However, the biomethane market has increased exponentially. You can see in this graph how the biomethane production increased exponentially from 0.5 billion cubic meter in 2011 up to 3 billion cubic meter by the end of 2020. The number of biomethane plants also increased simultaneously, and we have around 1,000. We had around 1,000 biomethane plants in Europe by the end of 2021. The biomethane market is dominated by water scrubbing technologies still, but closely followed by membrane separation technologies, and then chemical scrubbing and pressure swing adsorption. Okay. These physical chemical technologies that are nowadays available at commercial scale exhibit a economy of scale effect with a exponential increase in the specific cost at low treatment capacities, and we have to construct plants over 1,000 normal cubic meter per hour to reach stable specific costs of around 1,000 to 2,000 euros per normal cubic meter per hour of treatment capacity. Okay, so the real niche for research to decrease the capex of the process is plants below 500 normal cubic meter per hour. The energy demand, the electricity demand of physical chemical technologies is rather high, between 0.2 and 0.3 kilowatts hour per normal cubic meter of biogas treated for water scrubbing, pressure swing adsorption, membrane separation, or an organic solvent separation. Chemical scrubbing exhibit the lowest electricity demand, around 0.13 kilowatts hour per normal cubic meter. However, we need to supply approximately 0.5 kilowatts per hour per normal cubic meter of biogas in order to regenerate the chemical scrubbing solution or the organic solvent. Approximately 3 to 12% of the energy content in biogas is devoted to biogas purification, to biomethane. In this context, we identified a need to develop innovative and low-cost, environmentally friendly technologies in order to conduct a sustainable biogas upgrading in small to medium scale plants. Okay, the technology that we have been working over the past decade is photosynthetic biogas upgrading, which is based on the supply on the sparging of biogas, mainly composed of methane, carbon dioxide, and hydrogen sulfide, into a cultivation broth with a high alkalinity, high pH, where carbon dioxide and hydrogen sulfide selectively absorb. In the presence of light, carbon dioxide is photosynthetically fixed transformed into algal biomass with a release of oxygen, which is used by lithoautotrophic bacteria to oxidize hydrogen sulfide to sulfate. The nutrients needed to support both the growth of algae and the growth of bacteria can be supported by the liquid fraction of the diastates. Okay, and we produce an algal biomass that can be used as a bioenergy or as a biofertilizer feedstock. Okay, the process has been implemented in a two-stage process where biogas is sparged into an absorption column using the algal bacterial cultivation broth from the pond, from an algal pond, open algal pond, as a scrubbing solution. Hydrogen sulfide is oxidized in situ in the absorption column using the oxygen dissolved in the algal broth. The carbon dioxide dissolved is returned to the photobioreactor and photosynthetically fixed there. This is the pilot plant we used to validate the technology, both outdoors. It's a 180 liter hybrid algal pond interconnected to a 10 liter conical settler to remove the biomass, and a 2.5 liter biogas absorption column. One of the key parameters in this technology is the recycling liquid to biogas ratio in the absorption column, which was one of the first parameters we optimized. Okay, the first thing we did is a screening of the influence of the liquid to biogas ratio in the absorption column from 0 to 60. And what we observe is a complete removal of carbon dioxide, regardless of the liquid to biogas ratio. Interestingly, when increasing the liquid to biogas ratio, the methane concentration decreased from 95% to 80%, which was a bit surprising at the beginning, but when we look at the oxygen concentration and the nitrogen concentration in the biomethane, in the upgraded biogas, we realize that the methane concentration decreases due to an active stripping of oxygen and nitrogen from the algal bacterial broth. If we want to work with this technology, we need to work at low liquid to biogas ratio. And indeed, the nitrogen content in the upgraded biogas and the oxygen content decrease when decreasing the liquid to biogas ratio from 1 to 0.5, which is the optimum. Okay, methane concentration also increases when the nitrogen and oxygen content decreases. However, below a certain value, 0.5, for instance, in our case, the pH in the absorption column decreases, the mass transfer of CO2 deteriorates, the oxygen concentration, the CO2 concentration in the biomethane increases, and the methane concentration in the biomethane decreases as a result of this deterioration in the gas liquid mass transfer of CO2 in the column. We also assess the removal efficiency of hydrogen sulfide in the process. The high pH of these photobioreactors entail a high mass transfer and actually a complete mass transfer of hydrogen sulfide, regardless of the liquid to biogas ratio. We always obtain a complete removal due to the higher solubility of hydrogen sulfide compared to carbon dioxide. One of the parameters we also optimize is the alkalinity and the temperature, which are parameters that can vary in photobioreactors. The process, in terms of biomethane quality, operated better at high inorganic carbon concentration. At a high inorganic carbon concentration of 1,500 milligrams per liter, the methane content in the biomethane reached around 95%, with CO2 concentration in the biomethane below 2%, and concentrations of 500 or 100 milligrams per liter resulted in a methane concentration of 75%, with high CO2 concentrations. In this graph, the white bars represent a process operation at 15 degrees and gray bars at the 35 degrees, and there was no significant influence of the temperature on the process of biogas upgrading. This is a representation of the scale up we have been doing with this technology from a 100 liters indoor photobioreactor in 2011 Within the European project in cover, we scale it up to 32 square meters in the south of Spain. Okay, you can see the photobioreactor, the settler, the biogas absorption column. And right now we are validating this technology in the context of urban waste solid treatment in a 270 square meter photobioreactor within the European project Urbiofin. This is a close-up of the pilot plant in Chiclana. Okay. In Chiclana, in this pilot plant outdoors, we assess the influence of the type of wastewater. Okay, we tested domestic wastewater from the wastewater treatment plant and the liquid fraction of the diastate, and the higher alkalinity and the higher buffer capacity of centrate supported higher CO2 removal efficiencies compared to the removal efficiencies obtained when using domestic wastewater with low alkalinity, low buffer capacity to support algal bacterial growth and CO2 and biogas scrubbing. So we want to use centrates or diastates in order to supply the nutrients. We need to take into account that these wastewater are highly loaded in they exhibit high concentration of nitrogen between 600, 4,000 milligrams per liter, and phosphorus up to 500 milligrams per liter. Theoretically, with this concentration, we could reach algal broth densities of 7 and even 50 grams per liter. I mean, you all work with microalgae and know that at these high microalgae densities, the light does not penetrate. We have very low photosynthetic efficiency, high respiration, which requires the development of new operational strategies to operate these photosynthetic biogas upgrading technologies with real diastates. Okay, so the process we engineer and we have been testing is, requires a biomass harvesting unit, either a settler, dissolved oxy, dissolved air flotation unit between the pond and the biogas absorption column. In this way, we can actually decide how much biomass we waste from the process, and we can control the biomass productivity and the biomass concentration in the pond by wasting more or less biomass from the harvesting unit. Okay, we assess indoors the influence of biomass productivity by increasing the biomass waste from the settler on the total removal of nitrogen and the total phosphorus removal in the hybrid algal pond. And interestingly, when increasing the biomass productivity, the total nitrogen removal that was not influenced by biomass productivity. It remained below above 95%, and phosphorus removal also remained constant regardless of the biomass productivity. However, when we evaluated the real recovery of nutrients in biomass, of course, the assimilatory mechanisms were boosted by recovering more algae from the settler, and the abiotic mechanisms like ammonia stripping or phosphorus precipitation were less significant at higher biomass productivity. Finally, we did a basic sustainability analysis using the metrics from the British Institute of Chemical Engineers, comparing the photosynthetic upgrading technology that we have described with a conventional physicochemical technology composed of an activated carbon filter combined with a pressurized water scrubbing using a case scenario of 300 normal cubic meters of biogas. Key indicators of the technology: the need for light and the low efficiency of photosynthesis requires significantly more land per cubic meter of per hour of biogas treated. However, the energy consumption during upgrading of biogas is reduced from 0.3 kilowatts hour per normal cubic meter to 0.08 kilowatts hour per normal cubic meter. Similarly, the operating cost of biogas upgrading decreased from 0.2 euros per normal cubic meter to less than 3 cents of euro per normal cubic meter of biogas treated. So take-home message of this presentation: biogas upgrading technologies, biogas upgrading market is still dominated by physicochemical technologies that present high operating costs and high environmental impacts. However, the technology here described has shown similar carbon dioxide and CO2 removal efficiencies, a good robustness with lower environmental impacts, lower operating costs. the need for biogas pretreatment in terms of particle, water, or siloxane removal is less severe than their physical-chemical counterparts. The technology has been tested at pilot and demo scale with significantly good results. We are able to recover nutrients from diastates from wastewater treatment plant or urban solid waste with no inhibition of algal growth. Photosynthetic biogas upgrading allows for a simultaneous CO2 removal and hydrogen sulfide removal if alkalinity and pH are high. And the key parameters to control the biomethane quality are the alkalinity, pH, and liquid to biogas rich. Finally, we can implement, I haven't shown in this presentation, by implementing a simple control, process control strategy, we can increase process robustness. Okay, so that's all from my side. This is my email in case you want to contact me. If you visit our city, Valladolid, in the center of Spain, it's only 1 hour drive from 1 hour by train from Madrid. I mean, you are welcome. Thank you very much.
Yeah, very much, Roa. Thanks. You're very good. Interesting presentation. Also, I'm very excited to see that now you're doing such a huge, big, and large scale demo plant. That's brilliant. So I have 2 questions from the audience. So one question is that, I'm sorry for my window because the automatic control system I cannot control this. So one question is, can the upgrading system operate at night?
Can upgrading system? No, I mean, the high alkalinity of the system has a high buffer capacity. So carbon dioxide can be absorbed. The pH decreases during the night and then is regenerated, and pH is regenerated during the day. So, I mean, when operating at high alkalinity, high inorganic carbon concentration, the system is able to absorb carbon dioxide, which is regenerated during the day. So you need to dimension the hybrid algal pump properly to be able to increase back the pH during the day by photosynthesis.
Okay. This first question. Another question is that, why there was such a high level of nitrogen gas in the algae broth?
Yeah, I mean, the ponds are in equilibrium with atmosphere. I mean, at ambient temperature and with the concentration of nitrogen gas in the atmosphere, the dissolved oxygen concentration of nitrogen of N2 is around 40 milligrams per liter. So, I mean, in the biogas absorption column, the dissolved nitrogen and the dissolved oxygen strip out from the liquid to the biomethane. When the liquid returns without nitrogen or dissolved oxygen, is loaded again with the nitrogen from the atmosphere. So that's why you need to control properly the liquid that you are using as a scrubbing solution in the column to prevent high nitrogen desorptions.
Okay, thanks. Yes, very much, Ro. Thanks for a nice presentation. Okay, so
thank you very much.
Okay, thanks. So now, according to schedule, we will have 10 minutes, a break. But because of we are late than the schedule, so I propose just a 5 minutes break. Okay, so we come back around. We start presentation at 11. Past 20 past 11. Okay, so in the case we can catch some time. So we will have our next presentation will start at 11:20. Okay, yeah, very much. See you later. I just say that okay, we have a huge amount of audience participants in the live stream. I see there's 350 participants in China. So but I couldn't check how many audience on the YouTube. Okay, yeah, see you on the a few minutes later. Okay, so 20 past 11. Okay, please don't leave. So hello everyone. So welcome back. We go to our next presentation. So the presentation will be given by Dr. Hugo Pereira. So Hugo is innovation manager of the Green Collab, Green Ocean Technologies and Products Collaborative Laboratory. So Hugo is very active in research, so he has a very productive in publications, but also he's very active in in the industry. So today he will talk about improving the sustainability of algae production in commercial scale facilities. Okay, please, Hugo. So the floor is yours.
Okay, thank you so much. Can you see my screen?
Yes.
Hear well?
Very good.
Okay, perfect. Thank you so much. First of all, I would like to acknowledge for the kind invitation from the colleagues from Galway University to make this seminar. My name is Hugo Pereira, and I'm part of Green Collab, which is a collaborative platform in Portugal, a private non-profit association that aggregates companies and research institutions in Portugal. And today I will try to give you an overview of the strategies that we are currently developing to improve the sustainability of algae production in commercial scale facilities. Okay, so the presentation is divided in four main sections. First, I will try to briefly explain how we produce algae in our industrial scale facilities. Then to explain the strategies to improve the sustainability of the production inputs so that we can reduce the costs, and also strategies to improve the sustainability of the harvesting and processing steps. And then a final conclusions section. So to produce algae in the industrial scale facilities, we need four main inputs. We need air, CO2, nutrients, and water. And then we can choose two different types of production systems. We can either use closed production systems, such as photobioreactors, and you can see here the production facilities of all microalgae in the center of Portugal, and also of Necton in the south of Portugal. But we can also use open systems, and here a raceway pond and the thin layer cascade of the University of Almeria. A very important part in the sustainability of algae biomass production is the thermoregulation, because this is often overlooked, but we need large quantities of water to cool down our systems, particularly in the spring and summer season. The use of water for the thermoregulation is key to maintain our productivities. So after the production of the biomass, we need to separate the microalgae from the culture media. We can do this using different technologies. However, at industrial scale, ultrafiltration and centrifugation are definitely the systems most used by the producing companies. And after this part, we can either process the biomass into a dry powder using a spray dryer or a freeze dryer, or we can directly freeze the biomass into a wet paste. So our common products in the industrial facilities are either fine biomass powder or a wet microalgae paste still containing the intracellular water. So based on this very brief explanation, I think you can see that the production of microalgae is requires very specific equipments. And this is our main hurdle, because nowadays we still have very high production costs, and it's key to reduce these production costs by using different different approaches that improve our sustainability. So looking at the inputs that I've spoke before, I will try now to give you a strategy for each of these inputs that we are following to try to improve, on one hand, to improve the sustainability of the whole pipeline, and also to significantly reduce the costs of microalgae production. So regarding the first input, which is light, this is an easy one. Sunlight is definitely the only sustainable light source for industrial cultivation of microalgae. Nevertheless, we can still optimize this parameter. And for instance, in the scope of the magnification project in the facilities of Necton, we are trying to identify what is the optimum volume of culture per unit of area. So what is the optimum cubic meters that we can have in each square meter of ground area of implementation? And we made several trials, and here you can see the photobioreactors of Necton, where we added 2 more rows on the top of the photobioreactor. So we increased the production volume from 15 cubic meters to 20 cubic meters, while maintaining exactly the same ground area of implementation. So our hypothesis was that we would increase our aerial productivity while maintaining similar biomass concentration. So this is key for the industry to try to produce as much biomass as possible in a given area. And just to show some results, you can see trials running in these 2 photobioreactors. So we ran the same culture simultaneously, and you can see that the growth performance of the culture is very similar. We did this for 3 different strains. The pattern was always the same. The biomass concentration was kept, so the overall aerial productivity was increased by 25%, and this was a very good and important thing for Necton, because we really increased the productivities, and this is key for the company. For sure, everyone heard about the use of artificial light to grow microalgae. We have several works on this topic. In my opinion, artificial light can only be used in very strategic steps of the process. For instance, we can use LEDs to try to offset the night biomass losses that we have in autotrophic production, because during the night, cells under respiration, we see a big loss of biomass. And here is the work that we conducted in raceway ponds, in the facilities of all microalgae and Necton in the scope of the Algae project, where we had 3 raceway ponds. We made 3 independent runs, 1 raceway without LEDs, so our control, the black line, another raceway with the LEDs lit only during the night period, and another turned on for 24 hours. And the pattern is very clear. The more light we give to our system, the higher the concentration. But it was very interesting to see that if we turn the LEDs only during the night period, we have a very significant biomass concentration, increase in biomass concentration, and the night biomass losses are very reduced. And this was also very interesting. Nevertheless, artificial light can be also used, in my opinion, in 2 more steps. We can use to improve the scale-up, or as a finishing step for the induction of high-value metabolites, such as omega-3 and carotenoids. And we are currently developing solutions to try to use LEDs only as a finishing step in the end of the production. So the second input that I would like to ask actually are 2 inputs. So it's water and nutrients. To produce microalgae, we need massive quantities of marine and freshwater, depending on the target strain. And we also use large quantities of commercial inorganic or organic nutrients that also have costs. So the way forward in this part is definitely to use water from other industries. For example, and we will have later a talk on this topic, urban wastewater is widely used, microalgae to treat urban wastewater, also for swine wastewater. And this is an amazing approach, in my opinion, because algae can really clean the water and remove compounds that cannot be removed with other processes. Nevertheless, if we think of human nutrition, it's very hard to believe that this algae can be sold for the human nutrition market. So in this context, in Green Collab, we are now following more clean effluents. And in the scope of the algae cycle project led by Necton, we are now reusing the water and nutrients, for example, from agriculture. So in hydroponic production systems, they have a big discharge of water rich in nutrients, and it's a much cleaner drain water. And our results are very impressive. You can see here some pictures of the algae growing in hydroponic wastewater, and we have very good results comparable to the ones that we have with our standard commercial media. Another example here on the macroalgae part, for example, another associate of Green Collab, Alga Plus, uses the water from the aquaculture ponds which are located next to the facility. So they have water and nutrients for free. And this is a very interesting approach because they are able to produce high quality organic biomass in a very sustainable approach using an integrated multi-trophic aquaculture approach. So in my opinion, circular economy approaches are key for the future sustainability of the algae sector and are definitely the way forward. The third input that I would like to address is carbon dioxide. Inorganic carbon is key for the industrial cultivation of phototrophic microalgae. We need to add carbon dioxide. One solution can be to place the production facilities next to emitting source, and here you can see the facility of all microalgae, which is located close to a cement factory, and they are able to use this CO2. Another approach can be to capture the CO2 stored and transport to the production facilities. But very recently, in the scope of the ProFuture project, direct air capture systems are being developed, and this is very interesting. A pilot system will now be installed in all microalgae, and these are systems that can capture atmospheric CO2 and concentrate, and they can be installed in situ and delivered to the algae production. And it's really a very sustainable approach that still needs optimization, but we see a great future in this technology. And finally, and probably the most important, energy is our major economic and environmental cost. We use large quantities of energy to keep our algae in suspension, and definitely the way forward is to use renewable energies to improve the sustainability. And for example, Necton already uses 85% of the energy comes from the solar panels. And this is very important. Nevertheless, we can develop production techniques that allow to reduce this energy demand. And for example, in the scope of the Magnificent project, we tried to turn off the pumps of the photobioreactors during the night period. So if this is an unproductive period, why should the reactors be mixing? So we made a trial, and you can see here the results. And it was conducted in triplicate for 2 strains, one reactor with the pumps on during the 24 hours and another which was only on during the day. And you can see that the growth pattern is very similar, meaning that we are able to reduce by 33% the energy demand just by turning off the pumps during the night period. Another interesting approach is a Necton case study to develop an off-the-grid photobioreactor in the scope of the ProFuture project. So they now have this photobioreactor that you can see in this image, and it's connected to solar panels, and there's an automatism that only turns on the pump when a given level of irradiance is attained. So even if a cloud is coming through on the top of the photobioreactor, the pumps will go slowly. And this is also a very interesting approach because we don't want to use any energy from the grid. We want our production to be completely from renewable sources. So after addressing the strategies on how to improve the production inputs, I will just now very briefly go to the processing part. Harvest is still an energy demanding process. Both centrifugation and ultrafiltration have high energy demands. And for some algae, and this is a work that I've done during my PhD at the facility of all microalgae, we were able to develop a sedimentation process where, using a 24-hour step, we were able to remove 95% of the water and harvest the biomass through the lower end of the tank. Of course, this can only be done for a selected number of strains, which have a high density and can follow on the water column. Nevertheless, for other algae, such as Nanochloropsis, We are using other technologies such as electrocoagulation, and also very interesting, these new membrane systems that work with vibration or gravity that have very low energy costs, and we are now testing them, and they are very, very interesting for industrial applications. And finally, regarding the drying, we are using solar drying as a sustainable technique for the microalgae industry. You can see here the system that we are currently using in both companies. And to validate the potential of this technology, we have conducted several trials where we grow our algae in the industrial scale production systems. We have done these trials for 2 different algae, for Phaeodactyl and also for Nanochloropsis. And we used 3 different industrial scale drying systems to obtain 3 different powders. And then we analyzed the approximate composition, the fatty acids, pigments, and vitamins. And we would like to see what is the difference between all of these industrial scale drying systems. Here just to show the machines that we used. So we grew our algae in 100 cubic meter tubular photobioreactors. The algae were harvested using a high capacity ultrafiltration system. And the part of this culture was spray dried, while the other part was centrifuged and later freeze dried and dried using a hybrid solar dryer. And it was very interesting because our results were very surprising. If you look at the effect of the different drying techniques, for example, in Nanochloropsis, in the pigment profile, and here you can see that freeze drying always gave the best results, and this was expected. But it was very interesting to see that the solar drying has a very similar result, while the spray dryer clearly reduces the content of, for instance, beta-carotene. And the same pattern was found for Phaeodactyl. The fucoxanthin was higher in the solar dryer compared to the spray dryer. Of course, the freeze dryer is always the gold standard for drying. And these results, in my opinion, are a very clear indication that solar drying holds a high potential for the microalgae industry. We also analyzed other metabolites. For instance, in the fatty acids, we had no significant differences between the 3 drying processes. And our main concern is in the vitamins, where solar drying had lower results compared to both spray dryer and freeze drying, namely on vitamin D2, Q1, and vitamin E. Regarding the vitamins, we still need to troubleshoot and to try to really understand if we can improve to have higher vitamin contents in solar dried biomass. So in conclusion, very briefly, I would like just to say that commercial scale production of algal biomass still presents high costs, and this is a fact that we really need to improve in the coming decade. However, we have novel strategies that can really improve the economic and sustainability of the sector, and this is what we are currently following. In our opinion, the integration of inputs from other industries is the way forward. So we need to implement these circular economy approaches to have inputs that can help the growth of the algae, but also to treat environmental constraints of the other industries. And we believe that although significant advances are needed, algae are definitely a feedstock of the future with great potential for different biotechnological applications. So I would like to acknowledge everyone for all of the audience. Sorry, and if you have any questions, I'll be very glad to answer. Thank you.
Yeah, very much for that. Very interesting presentation. Particularly, you are sharing your industry.
Sorry, Shinmin, I cannot hear you. I think.
Okay, can you hear me now? So.
It's very low. I don't know if it's my problem.
Oh, maybe it's my own computer problem. Yeah, so yeah, very much for your nice presentation. I see you're sharing your industry experience. That's very good. I have 2 questions from the audience. So one that considering the application of biomass, one of the biggest problem is the contamination of crops. How do you deal with this? I suppose here crops means algae.
It's a very good question. Contamination is a big issue. It's something that people don't like to, to really talk about it, but contamination is a very big hurdle in commercial scale facilities. We have contaminations in all cultures, in all strains. Of course, we have ways to mitigate them. And the best way is really to have good practices in the production. For some contaminations, we know how to deal with them, depending on the contamination, but others, when they appear, there's nothing to do. So we need to just collect or harvest the culture before it's highly damaged, and we start again. But so it's very strain or contamination dependent. Some of them we know how to cope with them and how to really eliminate them from our systems. But for us, for others, and I will say an example, amoebas are a kind of microorganism that is really hard to eliminate from the system. We have some approaches that sometimes work, but is one of the contaminations that we have very hard issues at commercial scale.
Or just another very quick question that you mentioned that carbon dioxide capture from air. So, but the carbon dioxide concentration in air is pretty low. So, where is it costly to get enough carbon dioxide from air?
It's a good question. I have to be honest, I'm not very sure about the economics. We have 2 projects running with this technology. The pilot system will now be implemented in a production facility. From what I know, they made great improvements during the last 3 years, and the economic is much better now, the economics of the whole process. But to be honest, it's not something that I'm comfortable to give much more of input. It's very interesting, it's costly, but we believe that in the near future, we will be able to have a sustainable method to introduce CO2. And but we still need research, it's true.
Yeah, thanks very much, Hugo. Thanks. Yeah, thanks.
Thank you.
Yeah. So now we'll move to the next presentation. So the next 3 presentations are from my research group. So they will share some results we got from their CE funded research project. So the first presentation was given by Dr. Yuansheng Hu. So Yuansheng is a doctor researcher working in my research group. So he will, his experience in the wetland, wastewater treatment technologies, and marine biotechnologies. So Yuansheng, please.
Okay, thanks, Simi, for the introduction. Can you hear me good?
Yes, yes.
You can see my screen, right?
No, not yet.
Not yet? Let me check. I think I have shared it. Give me a minute, okay? Okay. Yeah.
Yeah, okay, now, yeah.
Okay, good. Good morning, everyone. Just a minute. I'm very happy here today to give a talk on auto-floating microalgae for wastewater purification and biofuel byproduct production. And this is a research funded by the Sustainable Energy Authority of Ireland. So first of all, I'd like to give an introduction about the auto-floating microalgae. The auto-floating microalgae I'm talking about here are microalgae that can flow spontaneously without the need for coagulation and external flotation gas supply. So why we want to select and cultivate auto-floating microalgae? The first motivation is to overcome the harvesting challenge. So microalgae are usually suspended in water, difficult to separate and harvest, which cause high harvesting cost, in addition to a number of other process control issues. And the second motivation was to select lipid-producing microalgae for biodiesel production. So microalgae growth rate is negatively correlated with lipid content. Therefore, it's difficult to maintain the dominance of lipid-producing microalgae in practical application, which is usually under mixed cultural conditions like this open pond system. So due to the low density of lipid, microalgae with high lipid content may flow spontaneously. Therefore, we hypothesize that selecting auto-floating microalgae may lead to the selection of lipid-producing microalgae. This is the photo HDR process to select the auto-floating microalgae. The cyclic operation consists of 4 steps: feed of flush medium, growth, separation without any mixing, and discharge. So the key steps to select the auto-floating microalgae was the separation stage and discharge stage. So during the separation, the auto-floating microalgae float to the water surface and form a flow layer here, where the non-floatable microalgae remain in the suspension. And after that, the supplement is discharged rapidly from the bottom. So this separation and joining pattern create a selective process enabling the enhanced production of auto-floating microalgae, since the non-floatable microalgae are repeatedly washed out, where the auto-floating microalgae are retained. And this is the lab scale photobioreactors. It has a total cycle time of 1 day with light and dark cycle. And the 5% CO2 gas was provided during the light phase. Mixing was provided, and the temperature value allowed from 15 to 30 degrees Celsius. We used this inoculum we used for this experiment. The inoculum was a mixture of wastewater-borne microalgae and the liver algae. So the algae mixture was highly diverse with more than 20 cyanobacteria, ring algae, and diatom species. But it had a negligible auto-flotation activity. And the culture medium was effluent collected from our wastewater treatment plant in Galway Island. The wastewater was adjusted to nitrate around 10 milligram per liter and phosphorus around 1 milligram per liter to mimic a typical tertiary effluent. And the photobioreactor was operated over 270 days under non-sterile conditions. And the cultivation process can be divided into 4 periods. Period 1 was the startup with a very short separation time of just 5 minutes. And period 2 maintained all the operational parameters, except that our refill operation, which refer to a rapid drainage of the microalgae suspension and reintroduced back into the reactor before the separation phase. And in period 3, we extended the separation time from 5 minutes to 60 minutes. And lastly, in period 4, we increased the light intensity and the CO2 supply. And also we performed the microalgae harvesting at 20% each cycle. So this is the result. During the startup, only limited auto-flotation activity was observed. The gray dot is the auto-flotation efficiency. And there was no flow layer formed during the separation phase. And due to the significant biomass loss, the biomass concentration rapidly decreased from around 2,500 to 150 milligram per liter. So in the second period, it was accidentally found that applying a refill operation could improve the auto-flotation efficiency. However, it was not efficient and stable enough, and the biomass concentration in the reactor remained at a low level due to significant biomass loss. A thin flow layer was observed after the separation phase, And some of this floating biomass show the lipid accumulation at this yellow golden spot. We obtained significant improvement in the autofluotation efficiency in period 3 after extending the separation time from 5 minutes to 60 minutes. And as a result, the biomass concentration in the reactor increased linearly to 840 from very low level of 100 milligram per liter. And we observed a clear water flow layer formed during the separation phase. And there was also significant change in the microalgae community. Yellow green filament Chipnema became the most dominant species. In period 4, efficient autofluotation efficiency was maintained over 6 months, although the separation time was reduced to 30 minutes from 1 hour. And to maintain a stable biomass concentration in the reactor, 20% of microalgae were harvested each day, which gave a CO retention time of 5 days. And we obtained our average biomass productivity around 270 milligram per liter per day, which is very good. We observed very stable microalgae community structure since period 3, with relative abundance of Chipnema above 82% on average. And this micrograph visually shows the dominance of the Chipnema. So we can really observe other algae species in the reactor. And we achieved very efficient nitrogen removal after the successful autoflotation since period 3. Interestingly, most nitrate was removed in the dark phase. So in contrast to the nitrate, phosphorus removal was much more stable over time. This may be attributed to other physicochemical processes such as chemical precipitation and absorption, in addition to microalgae assimilation. So next, we investigate the autoflotation mechanism. So why the algae can flow? Originally, we expected that autoflotation would be caused by high lipid content due to its low density. However, the results show it was not the case, as the autoflotation efficiency was not related to the total lipid content. And to further clarify the law of lipid in autoflotation, we established a mathematical model to estimate the cell density as a function of the lipid content. And the results show that a high lipid content near 70% is required to gain positive balance. So therefore, it's not practical to rely on high lipid content to achieve autoflotation. So since the autoflotation was not induced by high lipid content, other mechanisms were investigated. We observed abundant microgas bubbles attached on the floating microalgae biomass. And therefore, we hypothesized that the autoflotation was induced by microoxygen bubbles resulting from photosynthesis. And the results confirm this hypothesis. So the autoflotation activity was reduced significantly when the oxygen production rate was inhibited to 40% and decreased to 0 when the oxygen production was completely inhibited. So therefore, the essence of autoflotation was in situ gas flotation induced by oxygen microbubbles from photosynthesis. Then we explore the biofuel and the byproduct production potential. First of all, an interesting property of the autoflotation microalgae was the excellent dewatering properties, which was better than the settlable microalgae and much better than this planktonic microalgae. This is an important characteristics because dewatering and drying are most energy intensive and costly downstream processing steps. We investigate the biodiesel production potential with PG11 medium and wastewater plant effluent, and the results show that the auto-floating microalgae could attain high lipid content of 30 to 40% for biodiesel production after the optimization of the cultivation conditions. It's also an ideal feedstock for bioalcohols production based on the high carbohydrates content. We can easily obtain a carbohydrate content around 50% and even up to 70%. So it also have a good potential to produce value-added byproduct. One interesting compound is beta-glucans, which is the main storage compound of tryptophan. So beta-glucans are known to have many biological activities and wider applications in several industry factors. So compared to other macroalgae, the auto-floating microalgae in this study demonstrate a high beta-glucan contents of 29 to 31% of dry cell weight without optimization of the cultivation conditions. Another potential byproduct is these zero nanocrystals, which are promising biomaterials for several sectors like biomedical, engineering, food packing, energy, and electronic. Based on this, we can develop biorefinery approaches to co-produce advanced biofuels and value-added byproduct while achieving wastewater biolimitation and CO2 capture. Finally, just a little bonus for you. These are phototrophic granules formed by this auto-floating macroalgae. We don't know exactly the mechanisms why this granule found. And I'd like to thank Sustainable Energy Authority of Ireland for funding this research. And thank you for your attention. And that's it.
Yeah, very much, Yuan-Shen. Thanks. So any questions from audience? Okay, I see no the audience will reply.
Okay.
So yeah, thanks, Yuan-Shen.
Okay.
So then we move to our next presentation. So next presentation will be given by Sasha. So Sasha was a researcher in my group. Now she's based in China. So Sasha's research focus on biofuel and resource recovery from algae, and also with the iron and carbon microelectrolysis for nutrient removal from wastewater. So Sasha will talk about the low energy harvesting of microalgae with the electro flotation technology. Sasha, please. Hello, Sasha, can you hear me?
Yeah, can you hear me, Xinmin?
Yeah, I can hear now. So yeah, you can share your screen now. So.
Okay. Can you see my screen now?
Yes, please.
Okay, hello everyone. I'm Sasha from Professor Zhang's group, and today I'm very honored to report my research work here. So today's topic of my presentation is low energy harvesting of tryptophan by electroflotation without calculation. And as we all know, microalgae can use ammonia and phosphorus from the municipal wastewater digestate or some industrial wastewater as essential nutrient for growth, and achieving cost-effective wastewater bioremediation. So microalgae also have the potential to reduce greenhouse gas emissions by CO2 biofixation. From the atmosphere. Furthermore, microalgae biomass also is rich in carbohydrates, pigment, proteins, and lipid, so it can be used to produce the biofuels, microalgae food, or DHA supplement, and some other bioproduct. But the bioproduct broadly involved in several stages like biomass cultivation, harvesting, and bioproduct extraction. So due to the small size and the stability of the microalgae, it is a particular challenge to harvest microalgae from the cultural medium. According to previous research, the harvesting process could contribute 20% to 30% of the total cost. So it would limit the application of the microalgae-based technicals. Therefore, it is essential to develop effective and economic method to harvesting microalgae biomass. According to our previous research, like Dr. Hu just mentioned, we find that trypnema could auto-float. But according to our research, we found that the recovery efficiency is dependent on the biomass concentration and the cultivation condition. Like if the biomass concentration is low, it can recover well. But if the condition rapidly changed, for example, temperature decreased rapidly, or the ammonia concentration or phosphorus concentration in the influent increased rapidly, the recovered efficiency will be poor. So we want to find efficient and faster and economic way to recover trypnema. Maybe can recover the other kind of microalgae like trypnema. So because we, as like just mentioned, that trypnema can auto flotation. So flotation is widely used in the solid splitting process in water or wastewater treatment. It relies on the gas bubble attached to the particle surface to splitting the particles from suspensions. So effective bubble and particle occlusion and subsequently bubble and particle attenuation are important for successful flotation. Now, in some applications, a pre-coagulation or flocculation stamp is usually applied by dosing chemical coagulations to help achieve satisfactory harvester effections. But it will result in high operation cost because of the consumption of the chemicals. And the produced mental areas like ferric will live in the recovered biomass. So it may be toxic to the microalgae and handle the continued cultivation. So according to this, we do the experiment like we choose 3 kinds of trypnema, 3 kinds of microalgae. One is trypnema and the other is Sandomyces and Pandorina. And we find that trypnema had the highest hydrophobicity degree is over than 98%, and this can be regarded as hydrophobic microalgae. And the Panorama had the lowest hydrophobicity degree, is about 42.8%. So this is regarded as the hydrophilic microalgae. According to these results, we designed the experiment. The experiment was composed of two parts. One part is compared the performance of electroflotation in harvesting microalgae with different hydrophobicity degree. All the test was conducted at the same condition. Microalgae biomass is about 1 gram per liter, and the electrolysis and the mixing time is about 2 minutes, and the current is 0.3 amp. The other part of this experiment is electroflotation of the trypnema with a specific object of investigating the effect of current, electrolysis time, velocity gradient, and biomass concentration. So from the result, we can find that compared with the 3 kinds of different microalgae, we can find that the trypnema can achieve the highest efficiency is about 96.2%. And the Panorama, the lowest hydrophobic degree, even we extended the spreading time to an hour, its little biomass can be recovered. And the other, from the compression ratio, we can find that because of the small size, cell size of the centesimus, so this is benefit to reduce the space between algae cell and forming well-composed algae flow. But due to the weaker hydrophobicity, when the spring time become longer, it will cause the dispersion of bubble from the cell surface, so decrease the compression ratio. From this, we can find that the trypnema can be effectively recovered by electroflotation without calculation because of the high degree of hydrophobicity. So we do the experiment to compare the electrolysis and the mixing, which is important. So we can find that mixing is essential in the trypnema harvesting. We can find only 37% biomass can be recovered by only proved mixing. And if only use electrolysis without any mixing, little biomass can be recovered. This may be because that a certain degree of trypnema is self-aggregation, so it can recovered by only have the mixing. And we investigate the effect of the current, find that over 96% of biomass can be recovered. But if the current only have 0.1 ampere, they only have 28% biomass can be recovered. So to further understand the effect of the current on flotation, the maximum floating velocity of trypnema was calculated by the modified Gumbel's model. From here, we can find that when the current increases, the maximum velocity will increase, but when the current exceeds 0.4 ampere, it will decrease rapidly. So if in particular application, this needed to be to find a certain range of the current to harvest this kind of microalgae. And from here, we can find even at a low current, because this group current only 0.1 ampere. Even at this low current, the harvest efficiency could be above the 85% when the electrolysis time is over 4 minutes. From here, 4 minutes to 6 minutes, we can find that the biomass can be good recovered. So I also calculate about the biomass amount needed to be recovered is about 1.68 milligram per gram biomass if we wanted to recover the biomass efficiently. Under this, we compared different velocity gradient and find that the recovered is over 95%, except for the lowest velocity gradient. But here we also calculate the maximum compression and find that when the velocity gradient increased, the maximum compression also will rapidly decrease. So as we know that the biomass in the cultivation, the biomass concentration will increase. So when the biomass concentration increased from 1 gram per liter to 5 grams per liter, a longer electrolysis and the maximum time was needed. And the amount of gas per gram biomass required was calculated here, and also increased with biomass concentration. But if the biomass concentration is 5 grams per liter, the maximum flocculation is decreased. So this is we compared with other technicals on the microalgae harvest and find that centrifugation can achieve, auto centrifugations can achieve the efficiency microalgae harvest, but the energy consumption is higher than in the result in our study. And also the membrane filtration, the energy consumption is higher than our results. So this study investigated the impact of the microalgae hydrobility on the harvesting performance by electroflotation without coagulation, and we find that GPMA can be used by only have the electroflotation, and the energy consumption is lower, only 0.19 kilowatt-hour per kilogram biomass. Also, this work has limitation because we didn't do the other kind of microalgae, the feasibility of this electroflotation. And the other is why the effector of zeta potential or bubble size, they can affect the microalgae harvester I think it's need further investigation. Also, this work is supported by the Sustainability Energy Authority of our island. So thank you for your listening.
Yeah, very much, Sasha. Just Dr. Wagner just asked you ask several questions. So one is how do you measure the hydrophobicity? Is this constant for individual strains or depending on cultivation conditions? How does colonization and the growth of Treponema compare to the more common species?
Sorry, I stopped to try now.
How do you measure the hydrophobicity?
We use the method is effort, and we use the in the 6.8 nanometers, and to measure the absorber in sorry, is here. I will show this again. Sorry. So can you see my point?
So another question is that how does whether hydrophobicity of the Treponema changes with the composition or just a constant?
I think it's just is a constant, because if we use the it's only use the hydrophobicity constant. I think the bubble can attach to the cell surface and to floating to the surface and spreading the solid to the cultural media.
I think one question is that to measure the hydrophobicity of the Microalgae, is this hydrophobicity changes or is it constant? Whether it changes in different conditions or it's just a constant?
Sorry, I can't hear clearly.
Hi, Shimi, Sasa, maybe can I help to explain these questions?
Just one question. So is this?
Yeah.
I'm sorry. This I think my phone's a problem. So is this hydrophobicity constant, or it it is depending on the cultivation conditions?
So just for the first question of Professor Wagon, the hydrophobicity is measured by this microbial adhesion to hydrocarbon method. So basically, if the seal has a higher degree of hydrophobicity, it will move to the organic phase, organic solvent phase in a biphase system. And the hydrophobicity is basically determined by this seal surface composition. So, for example, this algae has a seal surface, seal membrane, seal wall with a high content of hydrocarbons. So it will experience high degree of hydrophobicity. And sometimes, occasionally, it can be related to the cultivation conditions. For example, the growth stage and this light and also nutrient status. But it's maintained. It can maintain for this algae. It's maintained stable hydrophobicity over time. Okay.
Thanks. I think we have time limit, so I think Dr. Wagner have another question, but I think you can contact Dr. Wagner later. Okay, now we move to the third presentation. Also, we're also given by Yuanshen. So Yuanshen will talk about how to use this autofill Microalgae for digestive treatment and carbon dioxide sequestration and biofuel production. Yuan-Shen, please.
Okay. Is my screen now?
Yeah.
Yeah. Okay. Just give me a minute. Hi, everyone. It's me again. In this presentation, I will talk about the integration of outer floating microalgae cultivation with anaerobic digestion for simultaneous digestate treatment, CO2 capture, and biofuel production. So, so this is the concept, as several speakers mentioned earlier. It's a good idea to couple microalgae cultivation with anaerobic digestion, because AD generated waste digestate, which is rich in nutrient, and also CO2 abundant of CO2 from AD. These two elements can boost microalgae growth and by providing free nutrient and carbon source. In the meantime, the microalgae cultivated using nutrient from digestate and can be used to produce biofuels through this nutrient recycling. So in this system, we have considered two biofuel production routes, the biodiesel production and the biogas production. The selection of biodiesel is because this is a drop-in transport fuel. And the selection of biogas is because biogas production from microalgae can be easily integrated with the existing AD facilities. So during the project, we have conducted a series of batch and semi-continuous experiments to investigate the growth characteristics of outer-floating microalgae in digestate and centrate, the centrate of sewage sludge, and the biodiesel production potential, and also biogas production potential. Originally, we planned outdoor testing system, but this was interrupted, unfortunately, by the COVID. So first, we investigate the effect of CO2 concentration on the growth of outer-floating microalgae. And the CO2 source considered was the flue gas of the CHP unit, which could have a CO2 concentration of 10 to 15% when biogas was directly used, or 2 to 5% when biomethane or natural gas was used. So therefore, we investigate three CO2 concentration of 2%, 5%, and 15% in batch test. And the results show that 2% CO2 was too weak to support algae growth in digestate. Even if we doubled this CO2 supply, the microalgae growth was still very poor. Possibly, there was a high mass transfer limitation with digestate, and 2% CO2 was not strong enough to overcome this limitation. And the 15% CO2 high concentration could promote initial growth of microalgae, but could be toxic, cause some inhibition to microalgae growth at a high gas flow rate. And we found that 5% CO2 is the optimal CO2 concentration for this specific algae, which sustained the rapid microalgae growth in digestate. Then we investigate the effect of digestive loading rate on the growth of microalgae based on ammonia concentration. We found that maximum tolerable ammonia concentration was around 250 milligram per liter. So if exceeding this concentration could result significant inhibition, for example, very long lactane and lower end biomass concentration. So this may lead to certain limitations for high strength digestate, like a pigmanu digestate, which has ammonia concentration around 3,000 to near 5,000 milligram per liter. So which requires a high dilution rate. But it may be more feasible for centrate of sewage sludge at the wastewater treatment plant, which has a relatively lower ammonia concentration. And there's abundant dilution water. For example, if treated effluent can be used as the dilution water to achieve the acquired dilution rate. Within the tolerable ammonia concentration, the outer-floating microalgae attain the biodiesel yield of 7 to 21% of GICL weight, and the biodiesel productivity ranging from 37 to 48 milligram per liter per day. So we compared the lipid or fats production and the inhibition slack of ammonia of this outer-floating microalgae with my other microalgae, common microalgae reported in literature. So in general, the outer-floating microalgae had a medium tolerance to ammonia inhibition. So there's different values as low as 100 for certain microalgae in some studies, and as high as 400. And this outer-floating microalgae can tolerate to 250 milligram per liter of ammonia nitrogen. In terms of this lipid production, the lipid content or fat yield of this outer-floating microalgae was not very high compared to other microalgae, but the productivity was relatively high if we compare with other study here, because the high biomass productivity of this microalgae. And the outer-floating microalgae could effectively remove nutrients from digestate, including like ammonia and phosphorus, with a removal rate of 20 to 40 milligram per liter per day for ammonia nitrogen, and 1 to 3 milligram per liter per day for phosphorus. It appears that pigmanu digestate could sustain a higher nitrogen removal rate, possibly due to its higher phosphorus concentration as compared with the centrate of sewage sludge. So we investigate the long-term stability of the outer-floating microalgae in centrate under different operation conditions in semi-continuous experiment. The reason for using centrate was the manual digestate was not accessible due to the COVID restriction at the time of this experiment. So in general, is the outer-floating microalgae maintained stable for around 160 days with auto-flotation efficiency above 75% under mixed culture condition. Then the outer-floating deteriorated and the culture was contaminated by unicellular green algae. So to figure out the issue, we conducted a batch test, and the results showed that the growth of the outer-floating microalgae in centrate was restricted as compared with the BG11 medium. So which indicates there was some growth limiting factors in centrate. So to identify these factors, we compared the main constituent of centrate with BG11 medium and found that the phosphorus and sulfur level was in efficiency in centrate. By adding sulfur and phosphorus, and the microalgae growth was fully recovered and even exceeded in BG11 medium. And dosing other nutrients in the BG11 medium led to no further growth enhancement. Therefore, it was identified that sulfur and phosphorus were key growth limiting factors in centrate. And the reason may be due to sulfur reduction during anaerobic digestion, which led to this zero sulfur concentration in centrate. And for the phosphorus, because for centrate is always will apply calculation step, and the phosphorus may be precipitated and not available in the liquid to as a growth medium. So if we use centrate as a cultural medium to grow microalgae, we should be careful and pay attention to these growth limiting factors. We measured the serial composition under different operating conditions and found that the lipid production, lipid content was lower than the value obtained in batch test. But it was very easy to obtain high carbohydrate content, which is ideal for biogas or bioalcohols like bioethanol or biobutanol production. So there is some experiments and problems maybe caused by measurement errors. So the carbohydrate could be higher in these samples. So therefore, we investigate the biomeasurable potential of the auto-floating microalgae in mono and cold digestion conditions by standard BMP test under mesophilic conditions with varying algae to pig manure ratios. We use anaerobic sludge sourced from AD plant as the inoculant, and this is the inoculant substrate ratio and the initial inoculant concentration. So these are low biomass characteristics for the algae and pig manure. In comparison, the algae biomass had much higher organic content and the carbon to nitrogen ratio. So here comes the results: the daily methane production and the cumulative methane production, methane yield, and degradability. So the mono digestion of microalgae displayed a lag phase of about 2 days, and the final methane yield of the microalgae was 293 milligram per gram VS. With a degradability of 61%, indicating a good potential for further enhancement. And we found that cold digestion with pig manure effectively improves the overall degradability with the highest value of 81% at Ag to pig manure ratio of 1:1, corresponding to a methane yield of 535 milliliter per gram volatile solid. To review the synergistic effect of cold digestion, we applied these 3 models to get insight on the reaction kinetics, first order model, modified compost model, and the cold model. First, we expand the which model fits the experiment data best, and the results show that both the modified compost and the cold model give good fitting to the experimental data. Therefore, these 2 models were applied for further study. To identify the synergical effect of cold digestion and the methane evolution in each condition was calculated according to the proportion of microalgae and pig manure applied in the cold subject. So if there's no synergical effect, the methane yield of the cold digestion should be the weighted average of these 2 subjects' methane yield in mono digestion. And we found that measured methane yields were always higher than the calculated values, indicating positive synergy. Just some more results on the algae to pig manure ratios in cold digestion, all showed enhanced methane production. So the highest enhancement, around 28%, was obtained at the algae to pig manure ratio of 1:1. And after digestion, we investigate the dewatering property of the digestive study in terms of a specific resistance to filtration. And we found that the adding algae can improve the dewatering property of the digestate after the digestion, which is good for further digestive variolization. So for the perspective, our results show that we can envision sustainable bioenergy production from nutrient recycling by coupling AD and auto-floating microalgae cultivation. But due to the relatively low lipid content and the high carbohydrate contents, maybe it's better to consider bioalcohols production as a biofuel instead of biodiesel or biogas production. And that's it. And thanks again and for your attention.
Yeah, thanks, Yuanshen. Thanks. Because of time limits, I think we are 25 minutes later than scheduled. So I think okay, we just skip with the question time. So now we move to our last presentation in the morning. So this will be given by Professor Gio Wen. Hello, Gio. So I know it's very early in America. Yeah.
Not a problem. Not a problem.
So Gio is director for the Food Research Center in Iowa State University. So his research focused on bioprocessing engineering, growing as sustainable food, fuel, and biomaterial processing technologies. So Gio is a co-founder of a Iowa-based company that used algae to mitigate water pollution while developing high-value products. So today we welcome Gio here today to share his experience to converting their lab scale research to the commercial scale facilities. Okay, Gio, the floor is yours.
Thank you. So can you hear me and can you see my slide?
Yes, I can.
Great,
yeah.
Great. So first of all, I want to thank Dr. Chen for inviting me for making this presentation. So because it's pandemic, we have not been able to share our research for a quite long time. But in the past few years, we did do quite a bit of work. So today I'd like to share about the most recent progress of our research and the commercial effort to make this process a commercialization. Again, my name is Gio Wen. I'm currently a professor at Iowa State University and working on the bioprocessing engineering perspective, like biofuel production, biomass bioenergy, and recently we work on quite a bit of the plant-based food production. And in the meantime, I'm also a co-founder of a company called Biotechnology. And this company, we have been working on really hard to commercialize algae-based wastewater treatment process. So today I'd like to share a little bit more information about the commercialization effort of our work. So here it shows that the nutrient problem, right, in water and the drinking water has quite a bit implication for human health and the environmental damage. And this picture shows that for drinking water, if you have too much nitrate in the drinking water, cause a variety of like a colon cancer or kidney cancer for adults, and for a baby, they have called the blue baby syndrome. It is caused by the high nitrate concentration in drinking water. And from the environmental perspective, high ammonium, high nitrogen, and phosphorus cause eutrophication problem. So this picture shows that in the Gulf of Mexico, there's a hypoxic zone. Basically, the zone has no oxygen, and there's a lot of, you can see a lot of dead fish here, right? And so if you see the historically, actually human take advantage of Mother Nature to treat their wastewater. For example, this is a pond, a lot of nutrients in the pond, and cause algal bloom, right? And then this algal bloom cannot sustain forever because the algae actually just consume nitrogen and phosphorus in this open pond, in this pond. And then after all the nitrogen and phosphorus used, and the algae cannot grow anymore. So, and then you see the water become clear. And then of course, all the algae biomass settled on the bottom of the lake, and some other bacteria will eat this algae biomass and then use a lot of oxygen. That's caused the hypoxic problem, which is oxygen deficient, and that causes a lot of aquatic life like fish or dead. So that's the problem. And so what we want to do is that we want to take advantage of the mother nature process to treat wastewater, but just to put into a correct place. So from this slide, you can see that if in the conventional wastewater treatment process, you have a nutrient entering the wastewater treatment plant, right? And then the wastewater treatment plant, most effort are used to remove carbon, but nitrogen, phosphorus, particularly the phosphorus, they do not treat very well, and then leave the wastewater treatment plant, and then just end up in the downstream water or river. And then this caused the accumulation of the nutrient in a certain area to a higher concentration, and caused that eutrophication problem, which I showed in that previous slide, caused a lot of algae growth, and which is not good. So what we want to do is that we want to take advantage of this natural process of algae growing on nutrient, but just a place in a correct place, which is inside the wastewater treatment plant. So again, you have the nutrient flow into the wastewater treatment plant, and then you establish an algae treatment process to remove nitrogen and phosphorus before you discharge this wastewater into, before you discharge this treated wastewater into a river, and then there's no nutrient in the mother nature. Of course, during this process, you also harvest the algae biomass, which is rich with nitrogen and phosphorus, and you can use this algae as solid fertilizer. So that's our whole concept. And for using this wastewater treatment, you use algae for wastewater treatment. But if you think that across the world, there are a lot of research working on wastewater treatment by algae, but there's really very rare, if any, implementation of the commercial at a commercial scale. So we never heard that there's a commercial wastewater treatment plant that they use algae process. So why is that? So why? What factor prevents algae adoption in the wastewater treatment arena? So, and there are several problems related with the related with the scale up and the cost. The first one is the large footprint requirement. And the conventional wastewater treatment process, you have to have a big land to accommodate the algae cultivation process, which is always like a big open pond. And because this light penetration problem, you have to build a very shallow open pond with large surface area. So which is hard to be implemented in a wastewater treatment plant because just the limitation of the land. And also there are some complex and unreliable operation issues. Based on, for example, based on our experience, we work with quite a bit of wastewater treatment plant, and those operators, they have just like high school diploma or this kind of operators. So it's very difficult to let those operators to run a very complicated algae cultivation process. And also there's a CO2 delivery or co-location requirement. And it's hard to have this CO2 source and wastewater treatment co-located together. And each year over the season, over the day, even over one day from morning to night, the unvariable wastewater flow in terms of both the flow rate and the nutrient concentration are also quite different. And also, once you produce this algae using this nutrient to produce the algae in the wastewater treatment plant, how you take off, what's the offtake agreement between the operator of this wastewater treatment plant and the algae production process is kind of difficult. So all in all, this causes quite a bit of problem for implementation of the wastewater treatment process, the algae process in the wastewater treatment plant in commercial scale. So in the past quite many years, my group at Iowa State University has been working on a new algae cultivation process. I call it revolving algal biofuel or technology. So here, this slide on the left shows that schematic diagram how this concept works. Basically, you can just regard this as kind of a vertical conveyor belt. Right? At the bottom of this belt, a small portion of this belt is submerged into a reservoir which contains nutrients and the nitrogen, phosphorus. And then you just rotate the belt from the bottom to top and from top to bottom, just rotate back and forth. And at the position 1, the algae can absorb nutrient from wastewater and then just rotates out of the water and then directly exposed to the sunlight and the atmosphere conditions. And in this area, the algae can directly absorb the sunlight and the CO2. And then they rotate back to the wastewater reservoir to continue absorb nutrient. So going this back and forth, the algae can attach the belt and keep growing and to form a very thick biofilm. And at a certain stage, you do not want to get this biofilm too thick because the light penetration problem, the inside of the biofilm cannot get enough sunlight. So you just harvest the cell from this belt, and at a certain depths, at the point 3, and you harvest the algae biofilm, and you also leave a certain portion of the algae still inside outside belt, so you can just go back and forth and regrow and reharvest, regrow and harvest. So this is the concept of a RB system, and on the photo on the right, it shows that a pilot scale or module of this RB system is not a single belt, but it's many belts, and just designed in a way that they can serpentine going back and forth, and from the top to bottom, just to go through the one pass of this in this unit. So, and then there's in the past years, we have been working on a variety of aspects of this RB system, and we believe there are quite a few advantages of this RB versus conventional algae cultivation pond or photobioreactors. First of all, in the first slide, I showed that you can simply harvest the algae biofilm by just scraping the biofilm out of it. So you can avoid the relatively expensive harvesting process from the open pond of the algae. And also, you can have a higher productivity within a certain confined footprint area. Footprint, I mean that if you imagine you have a sunlight just shine on the floor, and here it's just that small footprint, it's a small floor area. Because you simply, like analogy, I use analogy, you build a skyscraper, and to let a lot of people, human, inside this skyscraper, so each surface area is pretty small. So you have you can put a lot of people there. So here is a similar concept. You grow the algae vertically, so you use a very small footprint area. And also you can enhance the CO2 delivery, because once you rotate the algal biofilm out of the wastewater and then you expose to the CO2 rich environment, or even even just a regular air, atmospheric conditions, the CO2 can directly contact with this algal biofilm. So there's no need to for CO2 to do this very severe meet a severe problem of mass transfer in the liquid, because usually in the liquid CO2 transfer, you have to penetrate the gas liquid membrane in order to reach the algae cell in the liquid. But here you expose the CO2, you expose the algae to the CO2 directly in the air. And also you can, the last advantage is that you can separate hydraulic retention time and solid retention time, because in the reservoir of this RB system, you can control the flow rate and control the hydraulic retention time, but you can also decide when you harvest the cell, which is the solid retention time. And so these two parameters can be separated so that you can optimize the process. And here is the when we talk about commercialization of the process, people will always ask you, what's the value proposition, right? What's the true benefit or what's the value of the process? So here's the whole flow shows that we use RB system to treat wastewater, and we believe there are 3 values. The first one is, yes, you treat wastewater and remove nitrogen, phosphorus, and also actually you can remove some BOD and total dissolved solid and some metals using this algae process. And then you get algae biomass, you get clean water in the 3rd box. And then next one, you can dry, do a very simple, like just the sun dry, the algae biomass. And then you can do a pelletization process to create a lot of pellet, algae-based pellet. And you can use this algae biomass as a potential fertilizer. And of course, there are some other usage of the algae biomass, but our current focus is to use this algae as a fertilizer. And the 3rd benefit is that the algae growth, they will inevitably absorb CO2. So you can sequence CO2 from the air. So that's the benefit for the algae cultivation process for wastewater treatment plant. And here it just shows that in the current is based on some statistic data. It shows that wastewater treatment plant contribute about 3% of total greenhouse gas emission globally, and partially because the traditional wastewater treatment plants, they use a huge amount of electricity or energy for this aeration basin process. So it's use a lot of electricity. And also you rely on heterotrophic bacteria to absorb this nitrogen and to remove a BOD, COD, BOD or COD, but you also end up a lot of CO2 emission. So, and then if you change to algae-based water process treatment, you can use very low energy. As I said earlier, in that RB system, you just use you still need to use some electricity to drive the belt from the top to the bottom, but you very little energy because the belt does not need necessarily to be drive very fast, very slow, going back and forth. And also you can capture the CO2 and from the air instead of emit CO2 into the system, into the air. And also from the sustainability perspective, you have this polluted water, and then you have use RB system to clean water, and just use the algae biomass as resource recovery, and then reuse the algae biomass. So this kind of a circular economy create a lot of benefit on that. And then in the past years, we have been using this algae process to treat different locations of the municipal wastewater treatment plant. So we proved that the RB system can be implemented into different locations in this wastewater treatment plant. For example, you can put into the first stage is to remove or physically remove the particles, and then in the conventional wastewater treatment plant, you have this active waste sludge process to treat the COD and the BOD, and then you can implement RB system right here and remove nutrient as well as removes partially of COD BOD. And you can also put the RB system after the secondary clarification process. At that stage, there are still quite a bit nutrient, but less COD BOD. Algae will take over, dominant the microbial consortium in this RB system and remove nutrient. And also in wastewater treatment plants, majority of wastewater treatment plants, they implement anaerobic digestion process to treat that thickened sludge, bacterial biomass, organic solid, and then from that digester, you have an anaerobic digester centrate. So RB system can also use to treat the centrate. So we have been working using this RB system to treat to implement at a different municipal wastewater treatment plants based on their requirements, and we implement at different locations. And people will ask that different wastewater treatment plant have different capacity depending on the population, right? So the flow rate are different, and the loading of nutrient, of course, are also different. So how you can adapt your system to a different wastewater treatment plant with different capacities. So what we want to design is that we want to design a module system and standardize the process. And each module will have a certain surface area of belt and certain operation parameters. And it depends on the wastewater treatment plant capacity or how many populations we can simply add 1, 2, or many modules. So by this way, you can standardize the process and also make the manufacture process more efficient. And the next few slides, I'd like to take a quick example to show that several projects we have been working on. So the first project, this we call the Slater, Iowa. So, in the Midwest area in United States, there are quite a bit of small town, very small town, like 1,000 people. And so for these small towns, the wastewater treatment process is different from mechanical-based treatment process, which I showed a moment ago in the secondary treatment, tertiary treatment. No, those small towns, they simply use aerated lagoon to treat the wastewater. And in this photo, you can see that at the bottom, this is the from the bottom, from the top, you can see that there's a huge lagoon and several hundred acres just to treat wastewater generated by 1,000 population, right? 1,000 population. So it's not very efficient, large footprint area. And also you can see that, and here there's some kind of a greenish material. It's because in the summer algae grows. And as I said earlier, in the nature, algae actually, in Mother Nature create algae and just growing in its pond. It causes quite a bit of problem. So what we want to do is that we want to implement RB system. And for this, actually the whole population of this town has 1,500 people. 1,500, yeah, 1,500 population there. And we installed 15 horsepower driven the belt module system. So in the first slide, I show that here is the 10, right? In this one, here we have a 15 module to treat a population of 1,500 people. And here is the, well, this slide shows this, and I apologize. Yeah, so here's the anaerobic digester for treat metropolitan water reclamation district in greater Chicago area. And so this is quite obviously, it's quite different from the small town I introduced earlier, right? This city has like millions people. And so they absolutely cannot use that aeration pond. They use a very, actually very efficient mechanical system, primary treatment, secondary treatment, tertiary treatment, and then they collect all the sludge. Then they treat, they collect all the sludge and doing an anaerobic digestion process. And then because the size of this plant is huge, and just the anaerobic digestion centric each day the discharge is about 1 million gallon per day. So you can imagine how much wastewater, original wastewater in this treatment plant. So to focus on this 1 million gallon centric per day capacity, we built a variety of different size, different module of RB system. It's still kind of a R&D stage, but the city is very interested in implementing the algae process to treat their wastewater from anaerobic digestion centrate. And in addition to municipal wastewater treatment, we also implement the algae cultivation system in different industry to treat nutrient from industry. And unlike municipal wastewater, which has a pretty consistent nutrient profile, nitrogen, phosphorus, right? Each person generate how much nutrient per day. So it's pretty consistent, no matter you are talking about in in US or in China, in Europe. So it's pretty consistent. But for industry, it's quite different because the different industry use different processes. So we have to adapt our system carefully to meet those industry demands. And here just several examples of what kind of industry we'll be using. And we can use the RB system to use as, for example, a food industry or as pretreatment process. This food actually is a meat processing plant. They generate a lot of meat or wastewater, and they send this wastewater to. Sure. Yes. So because of time, I just skipped out that's a slide, but we can use this for treating wastewater in industry. And then lastly, I like to quickly show you that we use this algae biomass as the fertilizer treatment for fertilizer usage. So here it just shows the plant growth, right? In the algae fertilizer, you see that it's growing very well for growing the plant and the potatoes. And the last slide, I really want to show you that. So it shows that how we implement this process in the Slater, Iowa, in that 1,500 population. So here's the one module inside the system. And then you can see that this is a pond, and then there's a, yes, wastewater flowing into the pond, and then treated with RB system. And the belt serpentine design go back and forth. And then because the season, there's quite actually, you see the slide, it's not very sunshine day, so there quite a bit of bacteria there, but there are algae later on take over. And then this is the harvest algae. And then here's the pond, you see the pond. And here the small footprint, very small footprint. Yeah, because of time, I will stop here, and I'm more than happy to answer any questions. Thank you.
Yeah, very much, Gio. Very impressive, very impressive. So due to time limit, I just maybe one question. So the audience asks you that, you know, what kind of microalgae can attach to such a AB system, so with other contaminants such as pharmaceuticals, and also attach to algae biomass or not?
Yeah, we did not try to treat pharmaceutical wastewater because I'm not sure that will work or not. We are focusing on municipal wastewater and the food processing wastewater. And what type of algae? We do not have a very pure algae cultivation system. We just use Mother Nature. And even at the different locations, different Slater, Iowa versus Chicago, their wastewater, we just take the algae from the local pond and then just inoculate into this RB system, because that's the best species consortium can survive in these environments. And we do not intentionally control the algae species. And also, obviously, from the last video, you can see that there's not very necessarily very green. It's sometimes can be black, means that there's a lot of bacteria growing there. So it is a mixed process, including different algae species as well as some bacteria there. So we actually believe this is a very robust consortium rather than a single species. Yeah.
Okay. Yeah. Very much, Gio. Thanks. For your time limit, so there's some other questions. You know, the audience, if you have more questions, you can ask. Contact Professor Wen. You know, email him. You know, so I think he'll be very happy to answer you. Okay. Thanks, Gio. So now we have finished all the presentation in the morning. Now we go to the panel discussion. I'm sorry that, you know, we are more than 30 minutes late. So now I pass this to Professor Dagmar, Stenger. You know, she will chair this panel discussion section. Yeah, Dagmar, please.
Thank you. And I would just like to, I'm not on camera, sorry. I would like just to introduce myself very briefly. I'm Professor in Botany at the University of Ireland in Galway, and I have been also part of this SEI funded project. So just to maybe start off the discussion, maybe come back to the beginning of the session that we had this morning, to come back to the renewable energy. And maybe there's a question also for the the first couple of speakers in the sense of how can we make the contribution that algae obviously can make, how can we make it a reality? So how can we get algae, obviously there's a lot of things happening internationally, but how can we move this up to the next step? So what are the challenges that are there from your perspective, and what might be the next steps? So maybe anyone, maybe the first two speakers, maybe Conal could comment in this, or even Shane, in terms of where we should be going in our research, or what are the gaps that you see in a very practical sense?
Yeah, I'm happy to. Or Shane, do you want to go first? You might know a bit more on the biofuel side than myself.
Yeah, on the biofuel side of things, like you can see from the data we presented that in this area anyway, that algae-derived biofuel, there's nothing there at the moment. And the big challenge for any nascent technology is getting a foothold in the market and moving beyond pilot scale into commercial reality. I think some of the benefits that are there at the moment is that there is policy support there insofar as, you have an advanced biofuel target which explicitly has algae listed there. So that helps the whole position and gives you at least a foothold or something to grab onto if you are looking for commercial transition, to go, well, it is listed here. It is something that in the EU sense anyway, it has been pushed, and it is been preferred to crop-based biofuels or even to tallow and UCO derived biofuels. So, be it algae or other forms of advanced biofuels that are listed in Annex 9, they are the ones that have been pushed from a policy perspective that I think gives you some, I suppose, hope that there is potential for it. Like I've seen a lot today that, honestly, a lot of it's beyond my understanding of it. But what stands out to me is two things. One is the cost of doing it is very expensive, so commercial realities are tough. And secondly, and that Conal's referred to this before as well, is just be very cognizant of the sustainability criteria. So the energy required to convert algae into commercial scale biofuels has to be understood from the start, and economies and efficiencies have to be gained to ensure your energy consumption, particularly fossil-based energy consumption, is minimized.
Yeah, any other comments on that maybe?
Yeah, just much in the same as Shane was saying. I think it's market development has to be there, and as Shane had just said there, there's obviously very clear policy signal on sustainability and greenhouse gas emissions reduction. So in any research that's being done, if that's front and center, especially any policymaker, in summaries that's clearly outlined to them. So as much as the commercialization part is also that it's very clear that it's sustainable, and that's front and center.
Is there maybe anybody who would be able to comment on how it has become a reality, or close to reality, in other regions and other countries? Maybe some companies who are involved in this. Is there anybody who would be able to comment on this? Obviously, it takes a lot of investment, and is there anyone? No companies would like to comment on this.
It does take a lot of investment. First of all, I think algae biofuel has been talked for a long time, and there are cycles go up and down, and of course each cycle, sometimes we feel that we just reinvent the wheel, right? But each cycle, there's not a completely the exact same cycle. There are some advancements of the technology or advancements, and each cycle has different focus. And for example, about 10 years ago, people, more than 10 years ago already. So about 15 years ago, people get crazy about algae biofuel, making green diesel, making biodiesel, making things. So later on, and then energy price crash. And then nobody talking about algae anymore for a few years. And then recently, I feel that at least in United States, and the people began talking about algae again, at least from US DOE, Department of Energy, or perspective, they invest quite a bit of money to solicit the algae research again. So, but this time is a little bit different, and there are still a small section in the request for proposal said that focus on biofuel, but majority of effort will be sustainability or CO2 sequestration, this kind of focus. And also from fuel production perspective, I feel that more and more people realize that making dropping fuel from called HTL, hydrothermal liquefaction process is the way to go. Once you get this algae biomass, and how to get the algae biomass is still quite a bit challenge, honestly. And the production of the algae is expensive, still very expensive. But yeah, so there are quite a bit of research working on this area as well, and how to make the production more efficient. And the process I introduced today is just one of the many processes. But yeah, there are quite a bit like the harvest, increasing the harvest efficiency from the open pond, and some other attachment system. So yeah, so it's quite diverse. But I would say overall, I feel that number one, you do not want to talk too much about. I'm sorry, I shouldn't say that. You do not want to talk only on biofuel production. You have to integrate with some other benefits, and CO2 sequestration and wastewater treatment, as example. And number two is that I would see that the commercial biofuel production from algae is still midterm, at least a midterm or long short, and it's not going to be commercialized overnight. It's still a lot of effort, but yes, from sustainability perspective, there are a lot of opportunities working on that.
So to add to this a little bit, the important thing for biofuel production, which again the price can fluctuate and they can be rather cheap, is to increase profitability, viability, economic potential in that sense. And one of the ways to do that is co-produce expensive stuff as well as the medium to cheap stuff, right? So the co-production of biofuels with high added value products is one way to increase profitability. The other issue, of course, is an overall positive energy balance, and it was mentioned. I mean, there are steps that are overlooked sometimes, and they are important in reducing actually the energy balance. So a holistic view, which I think the community starts to be having, is very important in realizing this.
Yeah, I think essentially you have three legs to stand on. You have the reduction in cost of algae production by producing high value product at the same time. You have the benefit of reducing CO2 emissions, and additionally you can use algae to clean up or help the cleanup of wastewater. So in theory, it's nearly too good to be true. And the question, of course, is that realizable? Because maybe we could also maybe benefit from your experience in the problem of upscaling. We talked about it, a lot of lab scale experiments, and then but some larger productions are also underway. And I think that is really impressive that in some cases, it's a pity now a colleague from Portugal has left because they are obviously doing it on a larger scale. So does anyone have any experience other than obviously the wastewater, any other experience in the upscaling where maybe in a lab scale, the production has worked really well and you can optimize the production of several co-products, and then to take that next step to really not only a large scale pilot, but really to be efficient in a kind of commercial sense. Is anyone who would like to comment on that?
I can have so the main, I think, challenge here is changing from a closed system to an open system. Open systems, and then as we saw in several presentations today, are positive because they can give you the volumes, right? but they don't give you the control. And so, for example, there are things that increase significantly productivity, like again, adding a carbon source or controlling well the conditions and everything else that you cannot do as well in open systems. So this is a step change that needs to be made, and something we're also working on along other people too, is how to make open systems more efficient, because the easy thing is to say, okay, I have an open system, I let things grow and I take what comes out of them, but that's not going to give you the step change that you need for commercial production of things, right? You need the optimized and controlled version of production.
And in addition, of course, they have the problem with high value products in an open system that you may not be able to use for certain applications.
Provenance and other things, absolutely.
Yeah.
Well, I would say there's already, obviously there's other algae commercial system already available, beta carotene production, so Dunaliella, and it worked for specific reasons. So for example, Dunaliella, high salt concentrations, so that is kind of controlling the environment and stopping contamination. So it's maybe looking at those kind of systems and thinking why they work. There's other ways to introduce stresses. So you can look at using different types of nutrients which are not accessible to contaminants, so particularly the nitrogen source. But I think one important point is also to think about the difference in environment. I mean, where we are in the UK or in Ireland, I think you don't have the same opportunities that you might have in Southern Europe or a slightly more illuminated countries. So trying to, I don't think we can do everything here that you can do in other countries. And that's an important point to think about.
I would just like to add there actually are some really successful undertakings in Scandinavia, and they don't have much light at a lot of time of the year. And they're doing really well and really successfully in sort of CO2 capture and also absorption of metals at the same time, and then co-production of a high value product. It is possible. I think it maybe you need to be lucky to find the right species that you can actually do this with, but I wouldn't give up hope just because of location yet.
No, but I think it shifts what you do with the algae. I think biofuel production, I think it's clear that on its own, that's going to be really, really challenging. And I think we have to move away from that. At the same time, the high value product production, there's a limited market for them. So we can't all produce the same high value product, otherwise it won't be a high value product anymore. So we need to maybe think of the algae to be more a vector of producing different products and tuning them towards those different products rather than just looking at the same product all over.
And integrating this into providing different services at the same time. So that is the trick, of course, too. Yeah. Can we come back to the comment that was made earlier on the sustainability criteria for the source of energy crops? I think you mentioned in was Conal's talk or Shane's talk the different criteria, and that algae were actually negative in terms of the carbon balance, and if there's a chance of integrating that into any system from a kind of targeted research point of view. Was it Conal who mentioned this?
Yeah, so it's on mine. So a big concern at the moment it was on indirect land use change. So on a lot of first generation biofuels, we can have issues in indirect land use change. That's something that is quite a low risk in advanced feedstocks. So again, that's another positive for algae, and so it's really just if commercialization and the cost can't come down, it's trying to get together all of the positives and to be able to spin that as much as if there's going to be a price difference from one fuel to the next, what positives is there to try and get someone to want to choose that over maybe a cheaper fuel, but there's sustainability issues with that fuel.
Well, I can add to that. Yeah. One of the things, the way the directives are going is that at the moment we're in looking at blending mandates. So all you have to do is meet a certain greenhouse gas saving. It doesn't matter if you meet it by 1% or you exceed it by 1,000%. It's all given the same value. RED 3 is looking to move to a carbon intensity reduction. So for every extra gram of CO2 you save per megajoule, you'll get rewarded. So the likes of biomethane, which can have significant negative carbon reductions, particularly when it's coupled with CO2 capture, can give biomethane, as an example, significant value because its carbon savings are so much higher than that of traditional biofuels in the absence of carbon capture for traditional biofuels. So if there was carbon capture with algae production, then again, that value can be realized by an excess reduction in carbon. So it's a ton, it's euros per ton of carbon saved is the currency, rather than just a biofuel that meets a certain percentage reduction.
I think that's a really interesting point. And also, as you mentioned, there are other emission targets that could maybe combined with that. So ammonia reduction, is that something that might be useful or as a potential in that?
Yeah, there's potential in ammonia for particularly in the marine sector for as a use as a biofuel essentially. It's been looked at. I think the UK have some incentives for biomethane or ammonia as a development fuel. It's not something really in Ireland at the moment. While biofuels supplied to the marine sector can avail of certs, it's not something that's currently done. Not to say it won't happen in the future with further incentives, but it's not a massive part of our energy system at the moment.
Mm-hmm. There was a really interesting point made earlier in the last presentation, which was really, I think, valuable to all of us, and that was that sometimes the wastewater treatment staff are not trained well enough to implement this, or have no interest or no ambition to get involved in this. But obviously, you have experience, Professor, to overcome this problem. How did you get around this? How did you manage to get involved in this?
Good question. Actually, in the past, you can see that we implement several systems at the I call the semi-commercial scale. It's not a full scale, but it's pretty significant size. So I feel that most of the time we spend time dealing with those non-technical issues. And for example, implementing the algae system in a real small town and to potentially treat wastewater commercially it's completely different from a research in a research laboratory, or get some small amount of wastewater and bring to lab to whatever research you want to do. There's nobody cares that. But if you want to make commercial, for example, state EPA agency need to be involved. They have to approve your process. Even you can show all the data, and in the laboratory scale, they are still very skeptical. And I would say overall in this arena, people tend to be conservative, particularly you are dealing with the government agencies. And so you have to convince them that this is the new technology. Yes, there's a risk. Any new technology has a risk, but you have to have this kind of a risk-taking attitude to implement, to prove our process. And even you prove that it's possible, get failed. It is possible, but I think the very important thing is that to change humans' mentality, that take some risk taking and implement a new technology. That's what I learned. And meantime, when you talking with that's with the government agency, but meantime when you talk to local government, small town, right, town leadership, those people it's quite different. Also, they do not necessarily understand the very detailed technical side. You have to convince them that this is a promising technology, not just for sustainability issues or for CO2 or sequestration. It can bring the real benefit to you. The benefit, I mean the economic benefit. So because those people, they do not care too much about how much CO2 I can sequester. I just need to treat my wastewater to reduce the nitrogen, the phosphorus or discharge to below the limit. That's it. And so you have to show them my technology, or if I implement my technology or compare the competing technology, how much money I can save for you. So that is very, very important. And and then in the wastewater treatment area, I would say the technology are quite diverse. I would say, like small town, they use different technology versus large city. So you probably have to do a lot of due diligence to find a niche. In my presentation, I said that we use this technology to implement both a large city like Chicago and small town, which has only 1,500 people. But in large city, actually, we found that it's very challenging. Actually, it's very challenging because large city, they have a variety of available technology. They can choose, they can compare different technologies in terms of cost. But small town, yes, those technologies are there, but all are relatively expensive because of the economy of scale. So that's the reason we choose the modular design in order to reduce the cost.
Just out of interest, how long did the process take from you approaching them and to actually be implemented and actually be running?
Yeah, it's very, very difficult, honestly. In the past, like 2018, in one slide, I showed that in 2018, finally, called the Iowa Department of Natural Resources, they finally approved. They said that, okay, RB can be implemented in this town. And then we spent almost 4 or 5 years from the beginning to the end to convince them that we might have many meetings with, because with some support from governor, even the governor kind of provide a lot of moral support because this is a small business and the government wants to promote small business in Iowa, so there's quite a help. But even that, we spend quite a bit of time on that.
Thank you. One thing that strikes me amongst this, I mean, you have a number of agencies that might even be responsible for the different components. You might have one, certainly in Ireland, you might have one agency responsible for wastewater and nutrient levels and another one for energy. And maybe it would be an idea also for different agencies responsible for these different processes to consider some kind of collaboration in the future.
Yes. So in wastewater treatment plant, it's just like EPA type of environmental protection agency. The energy sector, that's not involved too much. But so the fertilizer market is relatively easier because it's very highly commercialized, marketing driven. But for wastewater treatment process or nutrient discharge, that's the government regulated. So it's very slow. We will probably have all this experience, right? Anything dealing with government is going to be very, very slow and inefficient. So we have a lot of problems in the past.
Thank you for that's really valuable experience there. I'm just conscious of time, so maybe we could just, if there anyone would like any final comments that they would like to add before we close the session. No, nobody has any urgent comments to make. In that case, I would just like to thank all the contributors to this discussion, and it was very interesting to pick up on some of the points that were made during the talks, and I really thank you for your contributions. It's very interesting and food for thought for all of us, I think. So I just hand over to Professor Zhang to close the session today. Thank you.
Very much. Very much for also for the very good discussion. So yes, I just I just chatted the numbers, who participation in this workshop. Actually, and we for the Zoom we would just got 50 around, but we got 460 in the live stream channel in China, in China. And because I don't know how to check how many people watching the live stream in YouTube, so I don't know the numbers outside of China. But I'm very excited to see that so many people from China are interested in this workshop, because we know that China is the largest greenhouse gas emitter in the world now. So, but China has set up ambitious target to achieve carbon neutrality by 2060. So I think it's very good, to see that Chinese researchers and industry join this workshop to see what's going on in Europe and and also it's good for this collaboration in future. And also I would like to thank other speakers, for sharing your knowledge and experience with us. And also, it's the panel discussion is so brilliant. We have learned quite a lot. And also, I would like to thank my PhD students, like Yajin, Bong, and some other students who helped me to organize this workshop. And also, so thank you much again for making this workshop a big success. And I look forward to seeing all in future face to face. Okay, bye.
Thank you. Bye bye.
Thank you. Bye bye.